Bir S. Bora sir, okay, for inviting this. Thank you very much, sir. And all the FDP coordinators. Let me share my screen and we can start the session now. So the session is 2 hours, right, sir?
Yes, sir. Yes, sir.
2 hours, and all the participants are, assistants, professors, or teachers in engineering colleges.
Yes, sir. Yes, sir.
Right? Okay.
Yes.
Yeah, you can see my screen.
Yes, sir. It is
But
visible.
not in full screen, right?
Yes, sir.
It is in full screen or not?
Yes, sir. Full screen. Yes.
Okay, then fine. Very good. Thank you. Okay. Yeah, today I'm going to talk about the collaborative demand response with virtual system operator. Okay. Yeah, first of all, the problem with this one is I can't see myself. Okay, when I'm okay. Okay, I want to tell few things before we start the lecture. Okay, if you have any confusion or if you, any doubts, okay, in between, you can unmute yourself and you can ask me. Okay, otherwise type in the chat box. Sir, coordinators, please help me to read the chat box because I can't see the chat box while I am presenting the screen.
Okay, sir. Okay, sir.
So anything in the chat box, please tell me. Then definitely I will answer that. Okay. If nothing in the chat box, if you want to unmute and speak, you can talk to me. No problem at any point of time. Okay. This session is planned for 2 hours. Okay. And my professors, okay, Professor M. Saidulu sir and Sailya Kumari madam. Okay. Under these two people, I did my PhD, and they always tell that, okay, whenever you tell something to the students or guest audience, okay, be specific. Okay, if you're telling something and you are going and they are not able to understand anything, okay, then it's a waste of effort. Okay, instead of telling something, fuse things to the audience. Okay, tell whatever the correct thing. Okay, whatever you want to tell in a proper way and such that they need to understand, and that will be helpful to them a bit at least. Okay, so today also I will tell in that way. Okay, I will explain everything in a clear and crystal clear actually. Okay, if you have any confusion, please ask me. Okay, today we are discussing about the collaborative demand response with virtual system operator. It can be in microgrid and it can be in smart grid, grid connected mode, or as well as the islanded mode. Both it you can operate. Now, first of all, before going to that, okay, how many of you understand the title? Collaborative demand response. Okay, what is meant by demand response? Anyone? Sir, all are teachers, I think, from electrical engineering department. Okay. So all are from electrical engineering department and EC computer science, right?
Yes, sir.
Yeah, good. Okay. Then you can answer. Electrical engineering people can answer this. What is meant by demand response? You can guess also actually. Anyone?
Hi, yes, good morning, sir. So demand response means that including the distribution set customer to participate and then they can run their load at the where there is a less
Very nice,
peak
very
demand
nice.
rate. Likewise, we can.
Okay, very good. Okay. Yeah, the objective of our demand response program is, okay. The problem is if you have the flat load, okay, the people who know these power system, basic power system, they can understand this. Okay, if you have the flat load profile, then no problem, no disturbance to the power system. Our base load plants will run throughout the year, okay, throughout the day without any interruption. Okay, everything is fine. Okay, but the problem is we don't have the flat load profiles. Okay, at some point of time we have the peaks and some point of time we have the valleys. I think something in the chart box, sir. Okay. Right? Yes. Yeah. Okay. Yeah, we have sometimes we have the peaks and sometimes we have the valleys. Okay, that is disturbing the power system. Okay, what to do? Okay, to remove that peaks and to fill the valleys, what to do? Okay, so that's the reason we have so many techniques. One of the technique is the demand response. Okay? So in this demand response, you see that in this case I'm using the real time pricing. Okay, adoption of real time pricing has encouraged the users to optimize their usage of electricity. Okay, so we have so many options to encourage the users. One of the best thing is everybody will concern about the money. Okay, that's the reason pricing is the one of the key role. Okay, if you want to if I want to meet that, if you want to cut that peaks and fill the valleys. Okay, electricity price is the one of the tool we can manage. We means, okay, system operator can do the can play with this tariff such that the consumers can change their loads. That is the I hope everybody understand what is the demand response that we are following. Okay. Yeah. So adjusting the personal electricity usage to coincide with the times of lower demand can save the consumers money. Okay, by taking advantage of the lower prices. Okay, we have the lower prices, then obviously all the consumers will, I mean, can use the electricity at the lower demand times. Okay, uh, I mean, we have the valley times. Okay, then what we will do is we will reduce the prices. Okay, they can on the loads and they can fill the valleys. Okay. The peak times we will increase the price. Okay, then obviously they will shut down the load. Okay. Then we can cut the peaks. Okay, so that is the demand response, basic normal thing of the demand response. Okay, very good. And all those things also I'm skipping because everybody know that peak shaving, whenever there is a peak demand response will reduce the peak demand. That is also known as the peak shaving. Okay. Yeah, the advantage of this peak shaving is, okay, peak shaving enables the power providers to meet demands without having to install the new generation capacities. Okay, for example, if you don't have, if you don't cut that, if you don't do the peak shaving, okay, the problem is to meet that peak load. Definitely, we need to install the new generation capacities. Okay, so if you cut that peak load, then no problem at all. We no need to install the new generation capacities. I hope everybody understands. Okay. Yeah. So what are the different type of demand responses? Okay. So if you see that we have the incentive based demand response. The incentive based demand response, this is like that. The different type of demand response. One, incentive based. Incentive based means here we will tell the all the consumers that, okay, why unnecessarily I need to increase the price and you need to reduce the change the loads. Okay, I can you please enroll to my program. Okay, we have one incentive based program. Okay. So whenever I told you to shut down your load, okay, please do it yourself. Okay, so we will give the incentive. Like that, we have some contract between the consumers and the utility. That is a we will give some incentive such that they will do them. Mostly controlled by utilities and require consumers to willfully enroll for the load curtailment program. Okay, at a particular time, if you want the load curtailment, we will do that. Okay. But the problem with this incentive based is, okay, nobody wants to join with that type of incentive based programs because even though they are giving some incentives, but they, at the time of their own, okay, they are cutting the our electricity. Okay, our electricity. So normally there is a problem to the consumers. They don't want to join. That is a drawback of this incentive based demand response technique. Okay. Next one is a price based demand response. That the thing, okay, already we discussed. Okay. In this various type of pricing survey, that is a real time pricing, time of use pricing, critical peak pricing, variable peak pricing, peak time rebate. Like that, so many type of the pricings are available. Okay. Among such pricing mechanisms, real time pricing is shown to be more rewarding to user base on their proactiveness, because whenever this is real-time pricing. If you see the real-time pricing, okay, we can understand that this time the electricity price is this much. Okay, based on that, the consumers can act. Okay, and they can shut down their loads or on their loads. Okay. So we are in this program, in this study. Okay, today's lecture, we are taking the real-time pricing. So, any doubts up to now? Hello.
Yes, sir. Clear, sir.
No doubts, sir.
Ah, no.
Very good. Okay. Now, what we are doing here is just now up to now we discussed about what is demand response. Okay. What is the price mechanism we are using? That is a real-time pricing. Okay. We are doing the demand response. Okay. So, in this study, in this class, okay, we are going to study the different type of consumers in a microgrid. Okay. That is industrial consumers, commercial consumers, and residential consumers. Okay. So we are taking for example, if you take the one microgrid, okay, one part of the microgrid we are considering as all are industrial consumers, okay, and one part is commercial, okay, one part is the residential consumers, okay. So now the problem is, see here, what is happening is, we are increasing the listen sir, this is the key point of the today's lecture. Okay, this is the problem identification. Okay, when you are doing the research or paper, okay, this is the main thing. What is the problem? Okay, and after that we are going to search for the solution. First we need to understand what is the problem. Okay, so here if you see that we have the different type of consumers are there. Okay, industrial consumers, commercial, and residential. Industrial consumers are very proactive in demand responses. Okay. Industrial consumers are very proactive because they want to reduce the price. Okay, they can run their industry at any time, no problem. Okay, midnight also they can on their loads, okay, off their loads, no problem. Okay, so industrial consumers are very, I mean, they keen about the money. Okay, so they are proactive in the demand response program. Commercial consumers, commercial means definitely at the time of the business they need to run the they need to on their loads. Okay, they're little bit active in the demand response. Residentials are not at all. Okay, so whatever the money you will give, residential consumers are don't want to off their minimum comforts, okay, in their homes. Because if anybody wants you to turn off your light at the evening 7 o'clock, would you like to turn off your load, turn off your light in your home? No, right? Okay. So residential consumers are the very less active in the demand response program. But we have all these three type of consumers are there. Okay. Now the problem is, sir, able to understand? Am I audible?
Yes, sir.
Okay. Now
Yes,
the
sir.
problem is, see that. Okay. So we have the some entity, okay, microgrid operator, okay, or a distribution system operator. Okay. He is a distribution system operator checking that what is the load at present time, what is the load at present time, and what is the generation available at that time. Okay, so depend upon the checking the frequency, you can easily tell that, okay, there is a mismatch between the active power generation and load. Okay, if no problem at all, okay, the frequency will within the limits. Okay, everything is fine. Okay, but suddenly the load is increased, let us assume. Okay, the load is increased. Okay, then what to do the system operator? System operator need to reduce the load, okay, or increase the generation. Okay, he is increase the generation up to his maximum capacity. He further he can't increase the generation. Okay, definitely something need to do on the load side, if you assume. Okay, so on the load side, hello, on the load side, to reduce the load, what system operator will do is real-time pricing demand response he is doing. Okay, so increase the price. He increased the price. Okay, so obviously because he increased the price, immediately the residential industrial consumers are they're proactive. Okay, they will shut down their loads. Okay, and the commercial consumers also at the off peak times, okay, If they want to participate, they can also contribute. The residential consumers also contribute a little bit. Okay, so altogether, suddenly the price is too low. I mean, the load is low now compared to the generation. Okay, so system operator will think that okay, it's unnecessary to cut off the generation. Okay, generation is I mean, he don't want to disturb the generation first of all. Okay, so that's the reason what he will do is because the generation is high and the load is low now. Okay, so what he will do is he will reduce the price. So able to understand? Okay, he will reduce the price. Okay, because the reduction of the price, these people will increase the load. Okay, so it is just like a conflict has tendency to kickstart a cycle, run and chase scenario. Okay, if you reduce the price, they are increasing the load. Okay, because of the increasing the load, if you increase the price, they are reducing the load. Okay, then when to stop? Okay, how we will know that? What is the exact price? Are able to understand the problem?
Yes, sir.
Yeah, then anybody know the answer what to do now? Okay. If we have the lower price, they are increasing the loads. Okay, because the increasing the loads, we are increasing the price. Because of the increasing the price, they are reducing the load. Okay. Because of the reducing the load, we are decreasing the price. They are increasing the load. Okay, like that. Okay, the prices are reduced, they are increasing the load. Okay, if the prices are high, they are reducing the load. Okay, so what is the solution? What to do now? Hello.
The load should be scheduled according to the price. That's all.
Yeah, but loads are not in our hand. In our means, with respect to system operator, I'm talking. We
No,
are the
no.
system
In demand response in US or Canada, whatever, the nowadays the 10% load they are taking by they are taken by the distribution companies. So loads are always, some portion of the loads are always in our hand.
Yeah, that's the reason. Okay, I don't want that type of things here. Okay, my research. Okay, I don't want to force the consumers. Okay, I mean that the 10% is there, sir. That is the incentive-based demand response. Okay, we are taking some portion of the consumer's load in our control, right? Hello, sir. Hello.
Yes, definitely.
Yeah, but we don't want that, right? Okay, I mean, are you happy if some person is controlling your loads? No, right? We are not happy.
At the end of the day, the customer is happy if he is getting some incentive and reduction in electrical
Yeah.
bill.
Very good, sir. Very good, sir. But in this case, in the real-time pricing, what is my solution? I am telling. Okay, if I mean, if you follow my lecture and up to 2 hours, next 1.5 hour. Okay,
Sure,
if
sir,
you
sure.
follow this one, the consumer is very happy, and same time system operator is also happy, and none of the loads is under the system operator control. Okay. Like that, that is the best solution compared to the previous one, right? Okay, so we are going to independent. Okay, our loads, our means, okay, as a consumer. Okay, my loads are not in the hand of the others. Okay, and same time system operator should not suffer. Okay, because there should not be any mismatch in frequencies. Okay, so the reason, is there any way to solve this one? Okay, I given a small try in this direction. Okay, I will explain to you that one today. Okay. Yeah. So before going that, what is the different type of? We have a different type of consumers, right? Industrial, commercial, and residential. Okay. So what is their behavior? I want to study the behavior of this industrial consumers, commercial, as well as the residential consumers. Okay. Let me skip all these things. No problem. I will explain. Okay, directly going to the industrial consumer. How the industrials are, consumers are there. For that, to analyze that one, okay, I consider the one industry that is oxygen generating station. Okay, oxygen generating systems, OGS. Okay? Why I consider this one is presently in this pandemic, there is a more lot of need of oxygen. I mean, to be frank, oxygen is more needed for the industry purpose only, not for the our breathing purpose. So, in this oxygen generating systems industry, I consider. In this, let us assume, okay, I taken some information from the reference papers how the oxygen generating industry will work, okay, with respect to the electrical point of view. Okay. So, yeah, in this, what I consider that oxygen generating
Sir,
solution.
excuse me.
Sorry.
Sir, sorry to interrupt you. Sir, which slide you are showing currently? I can see the peak saving slide.
Industrial load. You're not
No.
seeing that one?
Yes, sir. Yes, sir. Actually, the same slide. We are seeing same slide, the peak
change the
shaving.
slide, sir.
Oh,
Yes,
Now it
now
is
it is
okay.
industrial load. Now it is industrial load.
no. Let me. Yeah, you can see right now. I think you can see now, right?
Yes, now we can see the industrial load slide.
Now it is okay, sir.
Yeah. So oxygen generating systems. Okay, this is oxygen generating industry plant. Okay, some plant. Okay. What is their objective is, okay, they need to generate the 16,000 meter cube of oxygen every hour. Okay. Okay, 16,000 meter cube every hour. Okay, so in this, definitely they have some objective. Okay, some deadline is there for every industry. Compulsory this much they need to generate for every hour, like that every day or every hour. Okay, so for that purpose they have few things. Okay, uh, yeah, there is a schedulable oxygen generating systems and non-schedulable oxygen generating systems. Okay, in this we have it is having the 4 different oxygen generating systems. OGS one, probably you can understand this. Okay, OGS one, that is the non-schedulable. That means that compulsory it should run every time. Okay, because they have some deadline. Okay, compulsory they need to generate the some amount of oxygen every hour. That's the reason OGS one should operate all the time, non-schedulable. Okay, other remaining 3 oxygen generating systems, oxygen generation system 2, 3, 4 are schedulable. That means that whenever we want we can on those systems, whenever we want we can off those systems. Okay, whenever load is I mean the price is electricity price is very high, we will off all these 3 oxygen generating system 2, 3, 4. Okay, all things will be in off position when the electricity price is high. When the electricity price is low, then normally, okay, oxygen generation system 2, 3, 4 are on. Okay, yeah, that is the normal behavior of the industry load. Okay, so to be specific, further if we go inside, oxygen generating system 1, that is non-schedulable. Okay, if they want to yeah, operating point, okay, compulsory it should be on all the ways. Okay, because of that one only we can generate the maximum number maximum meter cubes of the oxygen. Okay, so the oxygen yield value is the 10,000 meter cube. Okay, because of the oxygen generating system 1, non-schedulable one. Okay, but we need to understand that if you want to generate that much of oxygen through that plant, oxygen generating system 1, okay, they required some amount of the cooling water demand. Okay, that is a 300 meter cube cooling water demand required to run the oxygen generating system 1. Okay, for that it is required electricity demand of 6,000 kilowatt hour. Okay, 6,000 kilowatt hour electricity demand is required if you want to run the oxygen generating system 1. Okay, but oxygen generating system 2, 3, 4 schedulable, that is in our hand. Okay, so if they want to participate in the demand response based on this oxygen generating system 2, 3, 4 schedulable oxygen generating systems are there, na? Based on this, and they can operate that oxygen generating systems 2, 3, 4 in the different operating points. Okay, for example, off mode, completely off. Okay, they won't generate any oxygen. Okay, they won't require any cooling water, and obviously no electricity demand required because no oxygen generating yielding. Okay, that is the operating point 1 off position. Okay, and operating point 8, the last one, if you see that operating point 8, that means that full capacity. Okay, it is running in the full capacity of 6,000 meter cubes of oxygen yielding. Okay, it required 70 meter cube volume of the cooling water demand. Okay, and 2100 kilowatt hour of electricity demand. Okay, that is 8th operating point, full running in the full condition. Okay, and we have the different operating points just like 2, 3, 4, 5, 6, 7, 8. Okay, hope you can see from the slide. Okay, yeah, if you are operating at different operating points, they have the different oxygen yieldings. Okay, and different amount of cooling water required and different amount of electricity demand is required. Sorry, is it okay? Able to understand the slide? Hello.
Yes, sir.
Yes, sir.
Yeah. So what they do is, whenever there is electricity demand is high, okay, electricity demand is, electricity price is high. Obviously, they will run the at one oxygen generating station 2, 3, 4 on the one mode, operating point 1. Obviously, this is non-schedulable. We can't do anything for the oxygen generating system 1. Okay, but yeah. Again, if you see that electricity price is high, but how much high? Okay, it is a very high. Then they will operate in the operating point 1. Okay, slightly high, then depend upon. Okay, you have different operating point, suitable operating point they need to choose. Okay, such that they can minimize the electricity bill. Right. Obviously, everybody will do that one. Okay, so here, if you see that this oxygen generating system required some cooling water, that also we need to consider. Okay, cooling water. So where we will get the cooling water? Again, we will have the separate plant for the cooling water. Okay, in this cooling water, okay, water cooling system, that is a separate plant. In that water cooling system, again, that is a schedulable water cooling system that also required electricity. So we have 3 different type of water cooling systems. All are schedulable ones. They can operate at the 3 different operating points. One means off position, production of cooling water is 0. Okay, electricity demand also 0. Okay, operating point 2, 100 meter cube of cooling water production, 28 kilowatt hour electricity demand. Operating point 3, 200 meter cube of cooling water production, 52 kilowatt hour electricity demand. Right. Okay. I hope you understand. Okay. So compulsory, we want the water cooling system should be run at appropriate times with appropriate operating point index, such that it required the it will generate the cooling water. If you have the cooling water, then at appropriate operating point, we can operate the oxygen generating system to generate the oxygen. Okay. Is that clear, sir? Everything?
Yes, sir.
So, but if you observe that, if you, for example, if you want to run the oxygen generating system OGS, okay, but compulsory, required amount of cooling water should be there. Okay, so those are the constraints. Okay, and for example, if the electricity price is very low, okay, we are generating the oxygen as well as the water cooling, okay, cooling water. But the problem is, if we generate the cooling water and as well as if we generate the oxygen, we need to store somewhere, right? Okay, if you don't have that storage capacity that much, okay, we need to limit again. Okay, that's the reason we have the constraints with respect to the storage also. We need to consider that one also. Okay, so oxygen generated. Okay, the stored oxygen should be between the OS underbar and overbar. Okay, there is a minimum reserve and maximum reserve. Okay, similarly for water cooling also we have the minimum reserve and maximum reserve. Okay, so in this, okay, see the next I mean, able to see the screen? Hello?
Yes, sir. Yes, sir.
For your understanding, a vectorial representation is given here for the complete industrial one industrial load. Okay, that is oxygen generating system. If you see that oxygen generating system here, okay, let me connect my explain. Just a second, 1 second. Yeah. So these are the things: OGS 1, 2, 3, 4. This is non-schedulable. You can't do anything. These are the schedulable. So these are the objectives. We need to control all these things. Okay, OGS 2, 3, 4. When to operate, when to not operate. Okay, all these things have the air input. Okay, and oxygen output. To generate this oxygen, we require the water cooling system. Water cooling system required. Okay, again it requires the obviously it requires the water, and it will cool the water. Okay, this is the cooling water storage is there. Okay, so to operate this again, okay, whenever see that, okay, if I am putting the blue color, that means that it is the our objective. This is a demand response. Okay, all these are participating in the demand response. We can modify the timings of the operation such that this can be participated in the demand response, right? Is it okay? So, but the load scheduler, okay, obviously this is the industry. Okay, they have some plan. Okay, so they know that they compulsory plan that when to schedule this oxygen generator system 2, 3, 4, and when to schedule this water cooling system 1, 2, 3. Okay, and they have separate. I already told you in the previous slides. Okay, they have operating index. Okay, when to operate, off position, 1 position, 2 position, like that. We have the different type of things are there. Okay, when to schedule. Okay, to do that one, they have some program. Okay, some intelligence mechanism compulsory they will adapt to this industry people. Okay, what they will do is normally, okay, they have the two backups are there. One is the any renewable generation itself. Okay, in the plant itself, is it any possible? For example, if some space is available and the rooftop also, they can put some PV panels. Okay, and they can generate the electricity. Okay, they have some PV panels and they can generate the electricity, and they can how much electricity is coming from the PV panels, that they will read. Okay, and they have definitely with the PV panels compulsory we need some storage, battery energy storage system. Okay, what is the status of the battery energy storage and how much is the battery energy storage? Okay, like that they have the battery energy storage system. Okay, now, and obviously whatever our objective is, it is connected to the system operator. The system operator, from the system operator we can receive the what is the price profile. Okay, what is the electricity cost now? So based on that, okay, listen carefully, this is important thing. Okay, we are assuming that every industry is having this type of mechanism. The thing is, they have some intelligence system that having the input of price profile, electricity price profile. Okay, and what is the renewable energy generation coming? I mean, what is the renewable energy available? Okay, that information will get that intelligence system. And what is the status of the battery? That information is coming, also received by that intelligence system. So based on these all three inputs, they will give the schedules. Okay, they will give the schedules when to operate this OGS 2, 3, 4 at what operating point, and water cooling system at what operating point they need to operate. So this is again there is a one optimization problem. Yes or no? Hello.
Yes, sir.
Yeah, the constraints here are, if you see that, Okay, so these are the inputs. They want to, they need to operate all these things. But again, while you are operating, we have some target. Okay, every hour this much of oxygen should generate. Okay, and again we need to see that oxygen storage also. If you are generating so much oxygen, where to store that oxygen? Okay, how much storage capacity we have, how much consumption we have. Okay, that also we need to take care, and water storage capacity also need to take care. Okay, so many constraints are there. Okay, this is a multi objective problem actually. Okay, when to operate and what operating points they need to operate, and meeting the so many constraints. So this is the multi objective problem. Okay, yeah. So in this, okay, to solve that multi objective problem, okay, I am assuming some assumptions. Okay, with the real time we are not, we no need to assume anything. Okay, but for study purpose I am assuming few assumptions here. Okay, if you see that we have the PV generation in the load, I mean in the industry itself. Okay, that PV generation at industry. Okay, for 24 hours how the PV is generating. Okay, in terms of, based on installed capacity. Okay, so let us assume this is a graph of the PV generation for the 24 hours. Okay, and with this we are having the some objective. Okay, to minimize, what is our objective? We need to minimize the cost of the electricity. Okay, cost of the electricity we need to minimize, that is our objective. For that we have the, we are build the some mathematical formulation for that. Okay, if you observe clearly, for hours 1 to 24 hours, okay, 1 to 24 hours, okay, this is NOGS is the number of oxygen generating systems. Okay, number of oxygen generating systems, those are controllable ones. Okay, non-controllable ones, non-schedulable we are not talking. Okay, the 1 to O is 1 to number of oxygen generating systems. Okay, at yeah, how much energy consumed. Okay, E naught TO is refers to the energy consumption by the OGS O through the operating index of TO. The oath oxygen generating plant. Okay, at what operating point it is operating. Okay, so that is the energy consumption by the I mean sum of all the oxygen generating system energy consumption. Okay, similarly the same way we can plan for the what is the energy consumed by the water cooling system plants. Okay, it also required, water cooling system also required some energy consumption. Okay, so how much it is consuming, this equation will give that one. Okay, and this is the BESS, battery energy storage system. Okay, so I mean gamma H represents the ratio of charging and discharging rate to maximum power rating of the BESS at our H. Okay, and EGS is the energy generation. Okay, in the plant at the hour of H. Okay, all this together multiplication of the electricity price at that hour H. Okay, and this is summation for the 24 hours. Okay, this equation will give the, okay, what is the cost of the total electricity consumption. Sir, able to understand? Any confusion here?
No, sir.
Okay, if you have any confusion, if you are not able to understand this equation, please ask me, I will explain. Okay, it is very simple, sir. It's simple maths. Okay, sigma H equal to 1 to 24 hours. So for every hour we are calculating what is the energy consumption. Okay, we are multiplying with the electricity price. We are repeating for the 24 hours, we are adding. Okay, so it will give the 24 hours what is the cost of the electricity to that plant. Okay, oxygen generating plant. Clear? Okay, while meeting all the constraints. Okay, while we are minimizing this one, compulsory we need to follow the so many constraints. Okay, we cannot fully discharge our battery, we cannot fully charge our battery. Okay, and oxygen generating, I mean we should not, we are storing, okay, we are storing oxygen. Okay, for that we need to check that how much full that oxygen is. Okay, and similarly water cooling also, the storage is meeting or not. Okay, that also we need to take care. Okay, the same thing written here. Okay. So what we are doing is how to do that optimization now. Okay, for that optimization, I am considering the one of the optimization algorithm, okay, BAT optimization algorithm used here. Okay, and it is for each and every hour. Okay, we are assuming that our variable here is the what operating point. Okay, what operating point the OGS2 should operate. Okay, 3 and 4 all should operate. Okay, these three represent the oxygen generating system what operating point, and these three are the water cooling system operating points. Okay, and gamma is the how much rate the battery energy storage should I mean it should discharge or charge or at what rate. Okay, based on the available of the renewable energy sources. Okay, so we are taking this as the I mean hope if you not understand, I mean if you don't know what is the optimization algorithm, okay, then it is a little bit difficult to understand. Okay, but no problem, you can assume that okay, it is having some input. Okay, randomly it will generate the initial population, some answers it will generate randomly. Okay, and after that finally it will give the some particular answer based on the some different criteria. Okay, some way it will solve the thing and it will give the some answer like that. You can assume if you don't understand what is on the BAT optimization algorithm. Okay, clear. So with this one we can understand that what operating point we need to operate. Okay, for that all oxygen generating systems and as well as the water cooling systems. Okay, and battery at what operating point we need to charge and discharge the battery such that we are minimizing this one. Okay, the cost of the electricity of the plant will be reduced. Okay, sir, it is clear. Is it clear?
Yes, sir. Yes, sir.
Okay, so that is regarding the industry. Industry is over. Okay, presently we are working with only one thing. Okay, we have three, we did only one. Okay, that is industry is over now. Okay, next one is the commercial. Okay, this commercial I'm assuming that okay what I consider here is the electric vehicle fast charging station as a commercial one. Okay, so in this, if you see that if you understand the electric vehicle fast charging station completely, you need to understand what is on the electric vehicles. Okay, the first battery powered electric vehicles are developed in 1834. Presently, we'll assume that electric vehicles are very new, but no. Okay, before the internal combustion engines, okay, there are the first battery powered electric vehicles are there. Okay, first of all, why we are going for the electric vehicles? We understand that we can know that okay, for every liter of gasoline produces the 2.3 kg of the CO2. Okay? So that much pollution we are generating, and the current transportation system is responsible to about 23% of the greenhouse gas emissions. Okay? So every liter of the gasoline produces 2.3 kg of the CO2. Okay, and we are assuming that not because of the transportation, because of the industry, some other things, there is more pollution. But for your surprise, the current transportation system is responsible about the 23% of the greenhouse gas emissions worldwide. Okay, so we need to concern a lot. Okay, compulsory we need to move to the electric vehicles. Okay, to reduce the this CO2 emissions and greenhouse gas emissions. Okay, so what are the different type of electric vehicles? Any guess? So if you want to do the electric vehicle fast charging station, you need to understand completely. We need to understand what are the different type of electric vehicles. So any guess? Okay, let me tell you. Okay, the hybrid electric vehicles. Okay, hybrid electric vehicles are powered by both petrol and as well as the electricity. Okay, the electrical energy generated by the its car owns regenerative braking. I hope everybody know that what is on the regenerative. In this hybrid electric vehicles, we have the two different type of vehicles: the mild hybrids and full hybrid cars. Okay, mild hybrids are mild hybrids is I mean, this is also hybrid vehicle. Okay, but this mild hybrids, if you want to run the car completely with the electric motors, that is not possible. Okay, these electric motors will support to the engine whenever there is an acceleration cruising purpose only. Okay, whenever there is some push required for the car, these electric motors will give, that's all. Okay, but if you want to run the car completely using the electricity, that is not possible with the mild hybrids. Okay, full hybrid cars is, yes, it can be possible. Okay, for some time. For up to some time. Okay, if you want to run the car completely with the electric motors, you can do that. Okay, with the full hybrid cars. Yeah, but the problem with the full hybrid cars is okay, if you want to run longer distances, okay, that is not possible with the full hybrid cars, because there is no provision to charge the electric vehicle battery from the outside environment. Okay, I mean, the electricity is generated only with the regenerative braking and charging the electric vehicle battery. Okay, so if you provide that provision, that is called a plug-in hybrid vehicle. Okay, to extend the range of the vehicle, they will do that. There is some plug-in for the outside. They can charge the electric vehicle battery using the plug-in. That is the plug-in hybrid vehicles. Can you guess the last one? Hello. Sir, am I online? Audible?
Yes, sir. Yes.
Okay. Now the last one is a battery electric vehicle. Battery electric vehicles are full electric vehicles. Okay, actually these are the electric vehicles we are talking today. Okay, they don't have any petrol engine, fuel tank, exhaust pipe. All these are not there. Completely, it is fully operating only with the battery. Okay, those are the battery operated electric vehicles. And why we need to study this battery operated electric vehicles? If you see that, okay, the 2015 IC engine vehicles are the 98% vehicles are the IC engines. Okay. Only 1% are the full and mild hybrids, and remaining 1% are the battery operated or plug-in hybrid vehicles. Okay. If you see that 2020, I mean, this paper is published in 2018, 17 or 18. Okay, so it is estimated that by 2020, okay, 88% are the pure IC engine vehicles, and 7% are the full and mild hybrids. 1% are the plug-in hybrid, and 3% are the battery operated. Okay, but for your surprise, okay, by 2020 itself, they are estimated, but now, okay, there are comparatively more. Okay, this not 317% are the electric vehicles, but little bit more than this percentage. Okay, by 2025, it is assumed that 68% are the pure IC engines. Okay, the remaining are the electric vehicles. By 2030, okay, if you understand, more number of electric vehicles than the IC engine vehicles on the roads. Okay, by 2030. But I am assuming that they are telling like that, but I am assuming by 2026, 27, by that time itself, we have more number of electric vehicles than the IC engine vehicles. Okay. So what are the problems with these electric vehicles for the current EV markets in India? Okay, there are so many problems. Charging time. Okay, how much time to charge? Okay, inadequate charging infrastructure. That's the reason we are mainly focusing today. Okay, and range anxiety among the consumers. Okay, high price of the electric vehicles and limited vehicle choices. And we are importing many components from the outside world. Okay. So these are the challenges presently. Okay, but all the challenges are slowly, okay, we are overcoming. Okay. If you see that the charging time, because we have the fast charging things are coming. Okay, we can easily, I mean, we can reduce the time of the charging. Okay, inadequate charging infrastructure. Okay, and imported components from the outside world. Okay, in this too, if you see that we have the Make in India programs presently. Okay, we are developing a lot and we are manufacturing so many things. Okay? So that's the reason we are overcoming that thing also. Okay? Driving range. Okay, now the electric vehicle driving range also increased. Okay, and the prices also reducing. Okay, you see that one by one. Okay, if you see that electric vehicle battery technologies, okay, energy density watt hour per kg. If you see that previously we have very low energy densities. Okay, presently we have almost 250 to 400 kilowatt hour per kg. So that much energy density. But the energy density, what it will give? Okay, for the lower weight, it will have a lot of energy you can store in the batteries. Okay. So that is the advantage of that one. Okay, if you see that, if you know the Telugu newspaper, okay, so there are the, I mean, if you know, in your local newspapers also you can understand that there are the so many Bahubali electric vehicles like that. Okay, they can charge the things within 15 to 20 minutes. Okay, completely. Okay, and capacity is also very high. Okay, it can run for the 20 lakh kilometer capacity, single battery. Okay, 16 years warranty. Like that, so many news are coming in the newspapers. Okay, you can see that so much development is going on the electric vehicles. Okay, so in this mainly I want to focus here is the DC fast charging. Okay, with the normal chargings, level 1 and level 2 charging. If you want to charge with level 1 and level 2, we can run for your car for the 10 to 20 miles range per 1 hour charging. Okay, but if you go for the DC fast charging, you can go up to 50 to 90 miles in 30 minutes charging, depend upon the what type of power capacity and make of the EV, all those things are there. Okay, so the DC fast charging, we want the DC power and DC voltage of around 480 volts and current of 125 amperes of DC. Okay, and yeah, prices also reducing drastically. Yeah, let me skip all this. Yeah, and this is the one of the slide I want to enlighten you. Okay. Hello, sir. Are you with me? Hello,
Yes,
everyone.
yes, sir. Yes, sir.
Yeah. Now see that don't forget what we are discussing. Okay, we are in the demand response. In the demand response, we already discussed about the one industry oxygen generating station, and second thing we are going towards the electric vehicle fast charging station that I am taking as a commercial segment. Okay, in that electric vehicle fast charging station, there is a need of the fast charging station compulsory because we want to charge the electric vehicle car battery very fastly. Okay, again, first of all, if you talk about the electric vehicle itself, we have some misconception in the outside world. Okay, so electric vehicle, if you see that, if you are charging the electric vehicle, okay, we are obviously we are charging through electricity. Okay, if the electricity is generating again from the fossil fuels, hello, let us assume fossil fuels only we are generating the electricity. Okay, not the renewables presently. Let us assume for some time. Okay, so fossil fuels we are generating the electricity and we are giving that electricity to the electric vehicle. Okay, and the same fossil fuel can be given to the normal IC engine car. Then what is the difference? Both are same, right? Hello.
Yes, sir.
Then why we need to go for the electric vehicle? Anyone?
Sir, can you just elaborate once again what exactly you want?
Yes, I will elaborate.
Repeat, sir, please. Once again.
Yes, I will elaborate. Just a second. Yeah. So we have the electric vehicle, right? Okay. The electric vehicle, where we are charging the electric vehicle from the electricity. I mean, we are using the electricity in the electric vehicle. Where the electricity is coming, we are again generating from the fossil fuels. Okay. Let us assume we are generating from the fossil fuels. We don't have the renewables presently. Okay. Hello.
Yes, sir.
Yes, sir.
Okay. But if you use the IC engine, we are also using the same fossil fuels in the car. Then why electric vehicles? Why EVs?
Sir, to reduce the emissions, sir.
Okay, in this both the cases we have emissions. Okay, in these emissions in the IC engine cars, okay, petrol and diesel cars. Okay, we are polluting everywhere. Okay, instead of polluting everywhere, okay, if you use the electric vehicle, we are polluting at one place, that is the electricity generating station.
Yes, sir. And apart from that, the transportation cost would also be more in case of when we go for the petrol or the gasoline based vehicle, because the transportation has to be either through by road or by rail or whatever it is. Whereas
Okay, so what we are talking about, transportation cost, right? Okay, let me write all those. Okay, yeah. So transportation cost. Okay, transportation cost. Any other things?
Maintenance cost is also reduced, sir.
Maintenance, how
Yeah.
maintenance cost will reduce, madam? Any elaborate, please?
For electric vehicle, maintenance is reduced rather than our petrol vehicle or a
So
diesel
you
vehicle.
are talking again with respect to some cost. Okay, very good,
Yes.
madam. Any other? So with respect to our point of view, pollution point of view, nobody is talking. Okay. Our thing, we discussed that pollution is our
yes, as
Pollution.
even during the transportation also it is getting polluted.
which one, sir?
In case of the IC engine, if you run the IC engine, then the transportation has to be through road or by road or whatever it is. Then there will be some pollution emitting
you
during
are
the
talking
transportation
about,
itself,
Right.
which is not there in case of the electricity
yeah,
transmission.
we can talk like this. This is a distributed pollution.
Yes.
Okay, distributed pollution. This is a concentrated one place. Okay, one place pollution.
Yes.
I mean, no green engineer will tell that, okay, this is better than this one, sir. Okay, anybody will tell that, okay, instead of polluting everywhere, you pollute at one place. As an engineer, can we suggest that? No,
No.
both are wrong only. Okay,
Sir,
Yes.
comparatively, it is less, no, sir, when we use EVs.
how, sir? I mean, one place you are polluting more.
More. Yes, sir.
You're telling like that only.
Yes, sir.
Okay, that is a thing. Okay.
Yes, sir.
Yeah, then any other? Definitely, if you have the renewables is there, then we will come to that later. Okay, next slide is that only. Okay, if you have the renewables, we have the more advantages. Okay, but if you don't have the renewables, then electric vehicles are waste. Guess it. I mean, try it. Sir. Yeah, I'm teaching this class, a similar type of classes, electric vehicle fast charging stations, from the last maybe probably 4 years. Okay, previous or that one, maybe 5 years back, I saw the similar things. Okay, why we are going for the electric vehicles? Okay, we are polluting at one place instead of everywhere. Okay, is this justifiable? Like just so many things in the Facebook, Twitter, and all those things. Okay, still, okay, still so many people believe that electric vehicles are not that much useful. For your surprise, yes. Okay, many people will think like that only. Why we are going for electric vehicles? We are polluting at one place. Okay. Okay. Any other things, sir?
If we look at the efficiency of the size of the component, then as we grow the size of the the central generator or whatever it is, then they can be operated at more efficiently compared to the number of such devices.
Very nice, very nice. Okay. So that is one important point. Actually, I want to talk about that only, efficiency point. Okay. Obviously, Yeah, that you want to talk today. Very good, sir. Efficiency. Okay. Any other things? Okay, think it, sir. No problem. Okay. You made my point. What I want to discuss, you already told. Okay. That's fine. But I am telling this. I already told you for the past 4 years. I am telling this type of classes. Okay. One student. Okay. Maybe probably some university. Okay. He given 10 different answers. Okay. Why electric vehicle is more useful than the normal vehicle, even though we are not using the renewables. Okay, 10 different type of answers. Okay. We already got the 3-4 answers, right? He given 10 different type of answers. I'm very happy by seeing that answers. Anyway, I'm not telling all those answers. You think about it. Okay, what is the advantage of electric vehicle over the normal vehicles if you don't have renewable energies also? Okay, one other thing is efficiency that we are discussing today completely. Okay, see that if you are not using any renewable, we are using the same petrol, not the coal also. Okay, same petrol generation. Petrol, from the petrol we are generating electricity. Okay, then we have the efficiency of overall efficiency of, okay, see that well to wheel efficiency. Well to wheel means the petrol wells to the wheels. Okay, how much power we are getting to the wheels. Okay, that is called the well to wheel efficiency. Okay, if you see that the well to wheel efficiency for the electric vehicle is 23%. The same thing, the well to wheel efficiency for the this IC engine cars is the 13%. Okay, see that maybe you can tell that, sir, how we obtain all these numbers? Okay, I'm not obtain all these numbers. I didn't do any research. Okay, from this reference I'm giving. Okay, and in this reference, if you see that the slides, the whatever the slide I am presenting, okay, that is told by the I mean very high researchers. Okay, I forgot his name actually. Okay, so he given that in that slides. Okay, you can refer to this one and you can see that. Okay, so 23% and 13%. Okay, so how much efficiency difference? It is the 10%. 10% efficiency difference. Okay, hope all our electrical engineers you can understand what is meant by 10% efficiency difference in electrical. Okay, electrical power. 10% difference. Okay, what we are doing, simply we are not doing anything. Okay, change your car to the electric vehicle. Okay, you are saving the 10% of the electricity. Okay, I mean 10% of the efficiency. Okay, power with respect to energy. If you talk 10% of the energy you are saving simply if you change your car to the electric vehicle. Okay, sir, this is the one of the advantage of the electric vehicle over the IC engine. Okay, if everything is common, the behind things are the exactly common. But for your surprise, we have the renewables. Okay, the beauty is with the renewables. Okay, if you have the renewables, then see the difference. Okay, if you have the renewables, electric vehicle, okay, the energy is generating from the renewables. Okay, then we have the efficiency of 74% well to wheel efficiency. Okay, the internal combustion efficiency is only 13%. Now you tell me, sir, I mean, by seeing this slide, definitely you will, as an electrical engineer, okay, what type of car you will buy? Hello?
Yes, sir.
Yeah, as an electrical engineer, as an engineer, first of all, okay, see that where is 74% well to wheel efficiency, where is 13%? Okay, if you want to, I mean, if you are concerned about the environment, okay, if you're concerned about the energy consumption, okay, if you are concerned about the energy wasting, you can see that 74 efficiency and 13%. That is the reason everybody throughout the world, they are much focusing on the electric vehicles than the IC engines. Okay, and in our India also we have so many campaigning is going on for the electric vehicles. Hope everybody know that. Okay, EV 30 by 30. That means that 30% of the sales should be EVs. Okay, by 2030. That is the objective. This is the oath taken by the Indian government in 2017. For that purpose, they are given the two schemes. FAME scheme, faster adoption and manufacturing of the EVs by central government of India. Okay, and the one scheme is already over in that. Okay, they spend very good amount. Okay, and the second scheme is presently going on. Okay, by 2030, we can understand that 30% of the sales are the India. Okay, in India, if you see that here, 30% of the electric car sales by 2030 and 100% of the battery operated electric vehicles in urban buses. Okay, the other reason, if you see that, if you come to our Hyderabad, nearby Hyderabad and all these cities, okay, slowly they are moving towards the battery operated electric vehicle buses. Okay, by 2030, our objective is completely we will remove the normal buses and we will all urban buses should be the battery operated electric vehicles. Okay, anyway, like that we have all the countries, okay, all the major countries, they are also moving towards the electric vehicle. Okay. Is it okay, sir? Any doubts or any confusion, any questions up to now?
No, sir.
Okay, good. Okay, so EV charging station. Okay, in this come to our problem, demand response problem. Okay, in this I consider the one charging station. Okay, here I considered charging station consists of 100 charging slots. Okay, and power rating is 30 kilowatts each. Fast charging station. It is a commercial complex. Okay, so yeah, a time span of 24 hours. It will talk with the distribution system operator to get the estimated price. Okay, here what is happening here? See that, sir. Okay, I mean, this is also again everybody will work for the money. Okay, as a commercial complex. Okay, what they will do is they are also having their own PV panel. Okay, their own battery energy storage system. Okay, and they are also communicated with the distribution system operator. Okay, to read about what is the price profiles. Okay, then what they will do is this is the charging slots, right? Charging slots. Okay, these charging slots went to, I mean, this is the communication line and as well as the power line. Okay, they have some communication to, I mean, both the communications, two-side communication, and two-side power line is also there here for the charging, because electric vehicles can charge or discharge. Okay, electric vehicles can charge or discharge. Okay, so while I mean in the next slides I'm going to talk. Okay, what it will do is load scheduling and pricing. The problem, the electric vehicle here also we have the some programmer is there. Okay, some intelligent system is there. What it will do is it will read what is available now the solar PV panel. Okay, what is the present status of the battery energy storage system, what is the present price profiles, all this information it will gather. Okay, and it will also gather that presently how many charging slots are free. Okay, presently how many charging slots are charging. Okay, presently how many charging slots are discharging. Okay, so based on that it will change the pricing. Okay, it will change the pricing. What it will do is, okay, depend upon this one, because it needs to get the profit, obviously, right? A reasonable profit. Okay, and same time with the price is very high. Okay, the distribution system prices are very high. Okay, what it will do is it will show directly the same amount with respect to the customers. Okay, such that they can while, I mean, for example, if we are the users. Okay, I have one car. Okay, I went to that commercial complex and I don't have any work with my car. Okay, so I charged and I need some charging. I'm charging my present status of SOC, state of charge of my battery is, let us assume, the 50%. Okay, my car battery status. Okay, so with moderate price is very comparatively low, so that's the reason I'm charging. Okay, suddenly for the next hour they announced that the prices are increased by 20% because of the high demand. Okay, what I will do is, instead of charging I will discharge. Okay, I will discharge. Instead of charging I will discharge, because I have enough SOC. Okay, and I don't have anything to do for the next few hours with my car. Okay, and I will put my car there. Okay, simply instead of charging I will tell them to discharge from the car and pay me the money. They will happy to do that. Okay, they will happy to do that. Simply they will take my charging, and I will tell that while discharging, up to this up to 40% you can take. Okay, I want 40% minimum SOC in my car, so they will maintain that 40%, and they will discharge the 10% of the SOC, and they will pay me. Okay, like that we can do. Okay, the similar way, while doing the charging and discharging, they need to announce some prices. Okay, that prices will be how the prices will generate. Okay, at what price I need to give to the customer, such that the customer, I should not lose my customer. Okay, and I need to get the more customers. Okay, and I need to improve my profit. My means with respect to this charging station owner I am talking. Okay, so I need to give that proper pricing. Okay, correct pricing. Okay, how to generate that pricing, that it will do. Okay, the intelligence program will do that one, such that they will. This is under again one optimization problem. So able to understand?
Yes, sir.
Yeah, this is a very good problem. Okay, electric vehicle charging station, we have so many constraints. Okay, so many constraints, and I should not lose the customers. Okay, and same time I need to get the profits, maximize the profits, while we are seeing the PV panel and as well as the battery energy storage system. Okay, so here also we need to see that that SOC of the charging station should be within the limits. Okay, and this is also same thing. We have the solar power generation in the campus. Okay, we are assuming that the solar power for the 24 hours. Okay, I mean this is the plot for the 24 hours. Yeah, and because this is not the actually real-time charging station. Okay, so for that I am considering a few assumptions considered in this charging station, because without these assumptions I can't continue and run the program. Okay, so the thing is, first thing is, in this case I consider that if any vehicle is connected to the charging port, okay, it remain connected for the 1 hour. Okay, at least, I mean, if you are connected, you need to stay here for the 1 hour. But I run the program for 1 hour. But if you want, we can go for the 1/4 of the hour. That means 15 minutes. Minimum slot we can change in the program. That is 15 minutes. For my easiness purpose, I consider it is a 1 hour. Okay, for every hour I am doing. But same thing we can do for the 15 minutes also. Okay. So when a vehicle is connected, that will stay for that 15 minutes. Okay. So discharging price offered to the EV is 90% of the charging price. Okay. For example, I'm charging my vehicle. Okay, charging my vehicle. Okay. Now the present price is that 100% price. Okay. And I want to change my decision. Instead of charging, I want to discharge. Okay. Then how much price they will give? Okay. They won't give the 100% of the price, because that we are using their infrastructure. Their means electric vehicle fast charging station infrastructure. Okay, so for that, I mean, simply if you are discharging and you want to give the full money, means they won't give. They have some rules for that one also. Okay, in this case, I consider only 90% of the money they will give, because we are using. The consumers are using the electric vehicle fast charging station infrastructure. For that, they will reduce the 10% of the. I mean, all things are the real-time pricings. With respect to real-time pricings, we are done. Okay, with respect to the real-time pricing, they will reduce the 10%. Okay, the total number of EVs to be present at the charging station is same as shown in the below figure. Okay, so for that, I mean. But initially I want to start my program. Okay, at that time I need to understand that how many vehicles are connected at that point, or how many are charging and how many discharge. Okay, if you have the real-time data, then it is very good. Okay, but if we don't have the real-time data, we need to assume. Okay, so for that purpose, I don't have the real-time data. I assumed initially this one. Okay, for the 1 to 24 hours, these are the discharging vehicles, they are discharging vehicles. Normally, you can understand that the charging vehicles are more than the discharging vehicles. Okay, initially, for one point of time, to start the program, I consider that this initial count of charging and discharging of EVs. Yeah. And one more important thing, one more observation we did here is the, okay, if I mean the price, for example, if you see that presently grid price is not changed, it is 0%, then 100% of the vehicles are connected. Okay, the zero change in the price, the number of one is the, I mean presently we have the 100% vehicles, number of vehicles, let us assume 100. 100% of the vehicles are connected. Okay, and there is no change in the price. The all 100% vehicles, all vehicles are connected to the system. Okay, so the problem is if you increase the price, okay, 20% of the price is increased. Okay, 20% of the price is increased. Okay, then how many vehicles we will lose? Okay, if you observe that, we will lose only, okay, 30% of the vehicles we will lose. Okay, the 70% of the remaining vehicles, whatever may be the price change, they will connect. Okay, if you see that, yeah, this is 0.9, right? Okay, 0.8, 20%. This is the, yeah, 15%. Sorry, this is 15% of the vehicles we will lose. Okay, so if you have the 40% rise, okay, if you understand this graph, you can see the losing the customers. Okay, if you increase the price, losing the customers, in this rate we will lose. Okay? The 40% increase of the means, okay, then we will lose that 20% of the customers. Okay, so able to understand this graph? This is important.
Yes, sir.
Okay, the same way, okay, if you decrease the price, this is the way the vehicles will join. Okay, the 20% of the right with another color, the 20% of the price is less, then we can add 15% vehicles. Okay, this is price. Okay, this is the vehicle number. Okay, the same way we have the 40% reduction of the price, then we will get the 20% vehicles more. Okay, so this is the thing we are observed. Okay, yeah, whatever may be the thing, okay, not greater than 20% of the vehicles. Okay. The maximum vehicles will change are the only 20%. Okay, irrespective of the what is the change of the prices. Okay, that is another observation. So with this, again we read the optimization algorithm. Okay, for maximizing the profit, okay, for h equal to 1 to 24 hours, this is the price of the charging of the any, okay, number of electric vehicles charging. Okay, the number of electric vehicles charging means we will get the profit, right? Okay, more vehicles are charging means they will pay to us, then we'll get the profit. Okay, this is the how much rate they are charging. Okay, this is the number of electric vehicles charging, cost of the that vehicle charging price of the vehicles. Okay, and demand, okay, minus, because any vehicle is discharging, that is negative to us. Okay, this much power they are discharging, number of electric vehicles discharging, and discharge price, we need to pay this price. Okay, this price I mean we are collecting this price. Okay, charging price. Discharging price means we need to give that price to the discharged vehicles because we are taking the energy. Okay, and same way battery energy storage system in the charging station maximum. Okay, at what rate we are discharging and charging the thing. Okay, this will change with respect to the discharging and charging. Okay, so electricity price of at that tower. Okay, minus, okay, energy generating at that charging station in the electricity price. Okay, here I mean in the previous case, if you observe that this electricity price is common for total equation. Okay, if you see that the previous, if you see just a second, yeah, see that. Okay, but this is, if you see here this function, this is the bracket, so this is electricity price is common for the total equation. But here if you see that, yeah, if you see that this is not common. Okay, because we have a different type of prices. Okay, this is the charging price, discharging price, and these two are the electricity prices. Okay, So there is a difference between the electricity price, charging price of the vehicle, and discharging price of the vehicles. Three different costs are there here. That's the reason there is no common. Okay, and I want to maximize this one. Okay, any I mean, able to understand, sir? Hello.
Hello, sir.
Able to understand? Okay. Any questions up to now?
Just I'm a bit confused between the charging and discharging. See, if we are discharging, then as you rightly mentioned in the previous one of the slides, that is a 10% of the difference. And then what is the difference between that charging, discharging, and energy price?
I understand. Okay. For example, one vehicle is there. Okay, one vehicle is charging. Okay. What we will do is for the charging. Okay. It will connected to our slot, the charging station. Okay, and it is paying to us. Us means as a charging station owner. Okay. Charging station owner, it is giving the dollars. Okay, this is the charging price, correct?
Yes.
Okay, the thing is, for example, if the same vehicle is discharging. Okay, the same vehicle is discharging now. Okay, it is connected to the charging station. Because it is discharging, we are taking the power. Okay, let me draw with this one. Okay, the blue one is the electricity. Okay, electric power. Okay.
Yes.
Here the blue one is written. Okay, EP.
Okay.
The red one, let us take, this is the dollars, money. Okay, this is money. Dollars. Okay.
Dollars.
Who need to pay to whom? The charging station.
Charging to the owner of the car.
Vehicle. Okay. Discharging price.
Yes.
Right. Okay. But what is actually electricity price? Electricity price is EP. Okay. Who decided this electricity price? This is the system operator told this price.
Okay.
Right. That is our demand response. System operator will give the electricity price. Okay. But what charging station is doing that? Because you are using my infrastructure, right? Okay. I am providing so many things. So that's the reason my charging price is greater than the electricity price.
Okay, fine. Got it.
Okay. That is number one.
That's what I was asking, that what would be the difference in that? Will it be of the order of 10%, 5% on that?
That is dependent on, that is not fixed, sir, here. Okay, I didn't any fixation of that rule. Okay, but the problem is if it is more than 5% or 10%, no customer will come into our charging station.
Yes.
Right. Okay. There is a market. Okay, there is competition between the charging stations. Okay.
Yes.
Instead of charging in my, let us say, instead of charging in my petrol bunk, they will go to other petrol bunk.
Yeah, definitely.
Okay, the petrol price is high. Okay, same thing here also. Okay, but reasonably high. Okay, maybe probably we can have 2% or 3% high.
Yeah, got
reasonably. It. Okay, but at the same time, here you see that.
Sir, one question.
Yeah.
Sir, regarding this charging station, any design criteria, different design criteria is there for charging as well as discharging the battery with the same station?
No. Design means you are talking about how the components inside and what are the inverters.
Yes. That means same charging station is there now. That means requirement is in one case right now. What we understand regarding the charging station, with the help of charging station, we are charging the battery of the vehicles.
Yes.
Right now, I think you are discussing about from battery of the vehicle. The
discharging is correct.
Discharging is there. So, is there any same charging station can be used or some
same charging, exactly the same point we can discharge. Okay, same point. Okay, connection is also no difference. Okay, the same wire without changing anything. Okay, simply if you change the I don't know what is inside thing. Okay, simply if you change the switch, instead of charging, it will discharge. Okay. Yeah, in the discharge price, I'm talking more with respect to the power system. Okay, I'm not going in detail what is components inside. Anyway, hope you understand. Okay, so discharge price. How the discharge price should be? discharge price should be lower than the charging price. Okay, because yeah, if I mean, for example, if everybody is coming to the charging station, if everybody wants to discharge, then how the charging station will get the profit? Right, if everybody wants to get the discharge from this one, and everybody wants the electricity price, okay, then we are not running charity, right? Okay, so compulsory the charging station should survive. Okay, that's the reason the discharge price is less than the charging price. Okay, if you discharge, yeah.
So one question is that,
Yeah.
sir, the discharge, whenever the batteries are discharging from the EV vehicles, the power which we get will be given to the utility, or it will be stored somewhere in the.
Very nice, very nice, very nice. Okay, that is the constraint here. Okay, because we are getting the I mean the discharge vehicle is there, means compulsory we need to maintain that equation. That what is that? Okay, how much power we are getting from the discharge vehicles? Okay, the same power can be given to these charging vehicles or not. Okay, if any excess power is there, that will be sold to whom? Okay, that system operator, and we need to give
Yes,
the
sir.
system operator, or what we need to do? We need to store,
Yes, sir.
right?
Also,
Yeah.
we can have one more option that we can the other vehicles which require the charging itself.
That
With
already
that
told
discharge
Naman,
it
this
out.
one. First one is that one only.
Yes, sir. Okay. Yes, sir.
Okay, the first one is that one only. Okay, with the discharging through the charging vehicles. Okay, so
Right, sir.
directly give to them. Otherwise, go give to the system operator. Otherwise, we can store the thing.
Right. Thank you, sir.
Okay, madam. Very good. Very good. Nice. Okay. So the same way. Okay, whatever we do, okay, we need to maximize our profit. That is our objective. Okay, as a charging station. So finally, everybody, I mean, the same time I mean, the charging station is run for the only two things. Okay, one thing is the maximize the profit, and second one is don't disturb the power system. Okay, it should not affect the power system. Okay, it should not disturb the power system. That means that it is taking huge. I mean, it is demand response actually in another way. Okay, it should well behave with respect to the power system, because it should not be overburdened to the system operator, it should not be underburdened to the operator. Okay, whenever the operator, it should help to the operator, to be frank. Okay, whenever operator requires some load, additional load, the charging station should give that load. Okay, whenever the system operator should ease that load, okay, the charging station should able to release some load. Okay, should take that load. Okay, I hope you understand. Okay, like that we need to run the optimization, and we need to do the both the things, maximize the profit as well as the good behaving with respect to the system operator. Okay, and I mean indirectly, that is we are running properly connected to the system operator, and we are doing the demand response properly. Okay, man, very nice. Okay, the same thing I also did for the, I mean, using the BAT optimization algorithm. Okay, at what rate I need to operate my system such that the maximize the profit and suitably run the demand response. Okay, that will give the solution for that one. The last one is the residential load. Okay, the last one is the residential load. Two parts are over already. One is the industrial load. Okay, in that industrial we talked about the oxygen generating system, and second one is the commercial load. Okay, in this we talked about the electric vehicle fast charging station. Okay, and third one we are discussing now, that is the residential load. Okay, and I already told that these residential loads, residential people are the not that much active in the demand response, because nobody wants to I mean, whatever we are doing, all the things only for live peacefully, right? Essentially in our homes. Okay, so if somebody tell that the electricity price is very very high, okay, you turn off your geyser, or you turn off your AC. Okay, whenever you're feeling, so obviously we will turn off your light. Okay, like that. If somebody tell that, okay, no, why we are doing all this thing for only for this comforts. Okay, so but if anybody turn off your washing machine, turn off your dishwasher, all those things, that can be possible. Okay, so that's the reason it is assumed that only whatever you do, okay, these residential consumers only they will support only for the 20% of the 20% of the demand response. Okay, not more than that. Okay, but if for your surprise, if you see that the industry is opposite, they will cooperate up to 80%. Okay, because if they cooperate, they will get more money. Industry, that's the reason, and they don't have any all or now automatic. Okay, whenever the electricity price is low, automatically it will on. Okay, whenever electricity price is high, they will off. Okay, they will more 80% they will cooperate to the demand response industry people, and only residential people will cooperate with the 20%. I mean, all these are not exact numbers. Okay, some random numbers. Okay. Yeah, so in this it is very simple for the demand response equation for the residential loads. Okay, what is the energy consumption at that hour, okay, and what is the electricity price for all the 24 hours for all the residential consumers. Okay. Yeah, now how to solve the thing. Up to now we discussed about 3 different things. Okay, but how to solve them? Our basic problem, first one. Okay, if everybody is, I mean, if your price is increased, okay, then everybody is reducing the load. If everybody is reducing the load, the system operator will increase the, I mean, decrease the price. If they decrease the price, everybody will increase the load. Then how to solve this one? Okay, so for that we will kept in a virtual system operator. There is a under we are introduced a one virtual system operator. It is not physically there. Okay, but it is acting as a virtual system operator. Okay, before doing that, see that this is a virtual system operator. This is the actual system operator. Okay, this is electricity market. The electricity market will give the day ahead schedule electricity prices. Okay, what actually we are doing real time pricing scenario we are doing, right? Okay, just like real time scenario, real time pricing, the electricity market will give the day ahead schedule price. Okay, that means that next day these are the prices as we are guessing, like that. I mean, guessing prices only, not exactly these ones. Okay, day ahead schedule prices the electricity market will release. Okay, then what virtual system operator will do is there is another system operator in between the system operator and the consumers. Okay, the consumer one, let us assume this is the consumer one is the industry consumer. Okay, industry consumer, this virtual system operator, what it will do is, for example, if these are the prices, then what you will do? Okay, what you will do? This consumer also, I already told you, na? Okay, this consumer also having its own intelligence price reduction program. It is also there. Okay, so they will run this optimization technique. Optimization until that this is my load profile. Okay, if these are the prices, then this is my load profile. Okay, then similarly, okay, with respect to this consumer, okay, similarly the same price profiles I will distribute to all the remaining consumers also. Okay, so based on their load profiles, they will return the load profiles. Okay, if this is the price, then this is my load. Like that, they will return these things. Okay, actually, to be frank, we are not imported this real-time pricing. Actually, they are not done that load profile. Okay, both the things are not done. Okay, a day ahead we are doing everything. Okay, if this is the real-time pricing for the next day, okay, then that next day will be given to this consumer and they will give the load profile. Okay, if these are the prices, then these are my load profiles. Okay, like that everybody will return. Okay, so based on that, then the VSO will be very easy task to do. Okay, the thing is, then it will change the thing. Okay, if the load profile is like this, then my change delta. Okay, let me in the next slide it will be there. Okay, anyway, I will explain here. Next, I will run the slides. So then, if this is a load profile, I mean, this load profiles are all the consumers will give the load profile, right? Okay, then obviously they will change based on the load profiles. There will be change in the delta. Okay, change in the price. Okay, the delta will be delta plus lambda delta. Okay, so there will be change in the price. Again, the change in the price will give the load profile to all the consumers. Okay, So there will be iterations going on. Okay, at some iteration we have some fixed price such that the load profile won't change. Okay, fixed prices. Okay, I mean, fixed price means, the VSO, the situation is going on so many times. At one particular time, okay, if we have that lambda such that we don't have change in the profiles. Okay, sir, able to understand? This is a solution. Hello.
Hello.
Sir, able to understand?
Sir, could you please repeat once?
Yeah, sure. Okay. So we have the day ahead schedule price is there. Okay, the day ahead schedule price, the virtual system operator, actually it is not there. Virtually we are programming this one. Okay, this day ahead schedule prices will be given to the all consumers. Okay, the consumers also have their own programs, just like we are did in consumer programs. Okay, they will do the optimization and they will give the what is their load profile. They will give that what is their load profile. Okay, based on their load profile. Okay, again there will be change in the prices. Okay, the change in the prices again it will give to all the consumers. Again they will run the program, they will change the load profiles. Okay, at one point of time after few iterations, okay, there will be a change, price. Okay, the change in the load profile is not there. Clear, sir?
Yes, sir. So what I understand is it is like a convergence kind of thing. So
yes, convergence only. Okay.
Okay.
Iterations are going on. At some point of time, it will be converged. Okay?
Yes, got it.
And for a particular lambda, there will not be any load change in load profiles. Okay.
Yeah,
so
sure.
everybody is satisfied with that. Okay. Hello. So that is the same thing, sir. Okay. Initially, we are starting with the delta naught. Okay. Initial load profile, day ahead load profile. This is okay. And with that one, anyway, all this I already explained. Okay. They will slightly change the things. What is the difference in the load profiles? Okay. With that difference in the load profiles, okay, where a small sigma is there, that is the demand elasticity of the demand elasticity. We will add that one, and with that one we will increase the price. We will increase the price. Delta lambda is there, that is the increase the price. Okay, if we increase the price is there, okay, then obviously next iteration the price will vary. Okay, the price will vary. Okay, so with this one we have the next iteration prices. Okay, the next iteration prices will be again given to the previous one. Okay, the same similarly. Okay, this is the prices, we'll give that one, and then we will get the next iteration load profiles. Okay, this will be run until what? Okay, until we will have the, okay, see that change in the price for the next iteration to the original price. Okay, we have some stopping criteria. Okay, somewhere we need to stop. Okay, maximum price change during any hour is under some tolerable limit. Okay, then we are stopping the thing. So will not be, there is no price change. That means that there is no load change, load profile change. Okay, no need to change the price, because if we change it also, the load is exactly same. Okay, so at point of time we'll close that one. So that is the our appropriate price. Okay, we need to give to the consumers. Okay, such that they won't change their load because they're happy. Okay, the same thing elaborated in the diagram, and this is already published paper. I will give my paper also. You can, okay, if you have any doubts after that, you can see step by step. Okay, and you can go through it. Okay, now let me explain the results. Okay, so within the four iterations, I got the convergence. Okay, the limit is, the epsilon whatever taken is 0.15. Okay, so if you see that grid electricity price, okay, initial price and final price. See that initial prices we have the peaks, final prices, okay, a little bit flatter compared to the initial prices. Okay, so without demand response with initial price, demand response with the final price. Okay, all the three outputs are given here. Okay, this is industrial, hourly demand, how it is changed. Okay, without demand response with initial price, demand response with the final price. Okay, I hope you understand what is meant by demand response with initial price. Okay, that is initial lambda we are circulated to the all the consumers. That is initial one. Okay, and after the VSO introduce and finalize the thing. Okay, after all iterations, convergence. Okay, that is the demand response for the final price. Okay. Yeah, and similarly, how we are using the battery energy storage system in industry. Okay, initially and finally. Okay, initial stage we are not at all using the battery energy storage properly to charge and discharge. And finally, if you see that, okay, we are properly charged and discharged the battery energy storage, and we use that battery energy storage well. Okay, similarly for the charging station hourly demand, okay, all those three are given here. If you see that so much without a demand response, okay, and with demand response, all the things are, all the demands are well within the limits. Okay. Yeah, the same thing. Battery we are using the battery compared to the initial. Okay. And charging prices at charging station. See that, okay, very high. Okay, charging prices are the initial charging prices. Okay, the final charging prices are comparatively low. Okay. Yeah, charging vehicles. Okay, final count because charging and discharging of the electric vehicles. Okay, and this is the residential consumers. Okay, residential consumers, you can easily see that they will follow it, but a little one. Okay, so we are cutting the weeks and valleys, both the things in this residential loads. Okay. Aggregated, okay, total combinedly. Okay, you see that all the things, all the three, what we consider, see that we are cutting the peaks. Okay, if you talk about the numbers with respect to demand response, without demand response, okay, mean load. Industry is the 8.450, charging station is 0.884 in terms of megawatts. Okay, residential load is 14.87, aggregated system is 24.2140. Okay, maximum deviation from the mean load. Okay, if you observe that maximum deviation from the mean load, this is important. 6.4368 combined all the things. Okay, a DR with initial pricing. Okay, this is the 4.9150. DR with final pricing, if you observe, 3.529. Okay, see the deviation, maximum deviation from the mean load. Okay, if you have the mean load, the deviation, weeks and valleys, peaks and valleys. Okay, if you see that, the maximum deviation is the 6.4368, reduce it to 3.5298%. See that how much peaks and valleys are reduced. Okay, with the demand response for the final price. But if you see that every sector also, industry, charging station, residential load, it is reduced. Yeah, your industry, it is little bit increased. Okay, and this is reduced, and this is also reduced. Okay. Yeah, and with respect to the cost, if you see that, okay, industry operating cost without demand response is very high. Okay, with demand response, initial final price is low. Okay, so they will get, see that, okay, euros per day, 4.59 into 10 cube, 4.87 into 10 cube. Okay, charging station net income is 2.8.052. It is increased. Net income is increased. Cost is reduced. Okay, charging station operating cost is reduced. See that how much reduced it is. Okay, residential load operating cost is, see that how much reduced. All costs are reduced. Okay, net system operating cost is reduced, 14.27 to the 13.0. Okay, so cost is reduced. So we have all the benefits. Cost is reduced, profit is increased. Okay, and as well as we are cutting the peaks and valleys. Peaks and valleys, okay, in the graph. Okay, we are cutting the peaks and valleys in the graph. Okay, sir. Yeah, the same thing is published, okay, in the IET Smart Grid Journal. IET Smart Grid, okay, collaborative demand response in smart electric grid with virtual system operator. Okay, it is a IET Smart Grid, it's open access only. Everybody can download, and if you have any doubt, you can contact me at any time. In 2018, it is published. Yeah, and conclusion, you can easily see that. Okay, I already concluded also. Okay, with this demand response with final prices, we already increased the income of everything and decrease the cost of all the industry and as well as charging station as well as residential consumers, and we are cutting the peaks and valleys, and we properly maintain the demand response. Okay, that's all from my side. If you have any questions, we have 8 more minutes. I'm happy to answer. Okay, if you have any questions, any queries, and any other things. First of all, is it properly understand, sir?
Any question from participants?
Yeah, good morning.
Good morning, sir. Sir, my question is, for commercial problem, you have used a maximize function, right? And for residential problem, you have used a minimize function.
Yes, but we
as
can
an
use
objective
both.
function, sir.
Yes.
So my question is how to decide that particular objective function, whether it is maximize or minimize.
No.
Like maximization is related to profit and minimization is related to loss, right?
Yes. Okay. Yes, madam. What you want to do that with respect to that we need to see. Okay.
My question is how to decide that objective function.
Yeah. Well, how I decide, I will tell you. Here in the industry, what is my objective is I want to reduce the cost. I want to reduce the cost related to the electricity in the industry. That's the reason I consider that is the minimization problem. I want to minimize the cost. Okay. For the second case, I don't want to minimize any cost related in the charging station. I want to improve the profit in the profit related to the charging station. That's the reason I want to maximize the profits. Okay, madam?
Okay, sir. Okay, sir. Thank you, sir.
Yeah, any other?
Sir, in chat box, one comment is there. Sir, please share this PPT and published paper to all. So,
yeah, sure. So, published paper, you can. I will share the link. You can already download. That is open access only. Okay, anybody can download. Let me do the one thing.
So there is one question in chat box.
Please.
When we charge or discharge battery at faster or slower rate, is there any effect on battery?
Yes, there will be effect on the battery. Okay, but the presently, let me first download this article. Just a second. I'm doing that one. Yeah, you can download that one. Please check it.
Okay, for the paper link is shared by Chandrasekhar sir in chat box. So anyone who want download can download it. There is one question, sir, in chat box.
Yeah. I can read now.
Okay.
I can read the questions. Okay. When we charge or discharge the battery at faster or slower rate, is there any effect on the battery? Yes, there is effect on the battery, but that is effect is I mean, up to our knowledge, okay. I mean, up to now, we are discussing that type of batteries. We have definitely charging and discharging effect, okay. But I understand from that from my colleagues from the chemical engineering department, okay, they are reducing that effect drastically, okay. I mean, recent innovations, they are telling that if you faster rate or slower rate, if you charge, okay, doesn't no, I mean, not that much effect on the battery, like that they are telling, but I'm not aware completely regarding that. But as per our studies, okay, as electrical engineering, what we are studying, definitely there will be a definitely effect if you faster and slow rate of charging and discharging. Okay, sir. Mayank Patil. Yeah, next question, Vaiba Parmar. Okay, which platform is program? Yes, MATLAB. I'm using MATLAB. I'm using MATLAB. Okay, for optimization also, I will write my own code for the optimization. Okay, sir.
So which yes, sir. So which optimization techniques are being used generally for this demand response
I use the
algorithm?
BAT optimization algorithm, madam, because I started with initially genetic algorithm and particle swarm optimization, and after that shuffle frog leap algorithm and BAT algorithm and combined shuffle BAT algorithm. Like that, we have done so many things. Okay, I use the BAT optimization algorithm for this one.
Okay, thank you, sir. And sir, one more thing. What we have used these virtual operators for day-ahead scheduling. Sir, is there something that it is also possible in real time?
Actually, I mean, my assumption is it can be possible in real time. Okay. Yes, ma'am, that is possible in real time. But may not be 100% efficient. Okay, there will be something will be there. We need to adjust at that time properly. Hello.
Okay. Yes, sir. Thank you.
Okay. Yeah. Any other things? So if no questions, can I? Okay. My contact details I will share you to everyone.
Okay,
Okay,
thank you,
my
sir.
contact details are shared in the chat box. Okay, anytime if you want any other questions or any other things, okay, I'm available all the time. My WhatsApp number is also same. Okay, sir.
Okay, thank you, sir. Thank you very much for sparing time for us from your busy schedule. The session is very much informative, right? You have discussed, explained everything in detail. So thank you very much, sir, for sharing your views, your knowledge with us. Thank you very much, sir.
Thank you very much. And thank you very much from my side also for organizers. Okay. And especially Shabir, sir.
Okay, okay, sir.
Thank you very much.
Thank you very much, sir. Thank you very much, sir.
Can I leave, sir?
Yes, sir.
Yeah, thank you.
Okay, now there is a break, participants. There is a break of 15 minutes. Now the next session that is on power quality issues in microgrid by Dr. P. N. Tekvani. So the session will start from 11:45 a.m. sharp. And also participants are requested to fill the feedback, right? That is available on the chat box. So feedback link, day 2, session 1. Thank you. Good morning, sir. Good morning, Tekvani, sir.
Haji, good morning.
Good morning, sir. Good morning.
Very good morning to one and all. On behalf of the entire team of FDP and the Electrical Engineering Department SCET, I warmly welcome our eminent speaker, Dr. P.N. Tekvani, sir. He is presently working as a director, Directorate of Research and Innovation and Dean Faculty of Doctoral Studies and Research of Nirma University, Ahmedabad. He also serves as a professor of electrical engineering at Institute of Technology, Nirma University. He received his PhD degree from Indian Institute of Science, Bangalore, with Tech Corporation Medal Award for the best PhD thesis. He is the first rank holder in ME and university first in BE and also a gold medalist. In his professional career span of more than 25 years, he has worked for MTech Electronics India Limited, Gandhinagar, Electrical Research and Development Association, Vadodara, and Nirma University at various positions. During 2012 to 18, he served as chairman of Board of Studies of Electrical Engineering, Electronics and Communication Engineering, and Instrumentation and Control Engineering programs, as well of Nirma University. He has also worked as Director, Institute of Technology, and Dean, Faculty of Technology and Engineering of Nirma University for the academic year 2015-16. He is a member of Academic Council of Nirma University, Senior Administrative Officer in the Internal Quality Assurance Cell, PG Program Coordinator, and Professor in charge of Industry Institution Interaction Cell of Institute of Technology. His area of interest are power electronics, machines, power supplies, solar inverters, energy conservation, multi-level inverters, drives, active power filters, power quality, and smart grid. He is the recipient of several prestigious awards like Professor Muhammad H. Rashid Best Paper Award in 2017 in IEEE International Conference, Rajaram Bapu Patil National Award for the Most Promising Engineering College Teacher in 2016, and so on. He has authored more than 100 national and international research papers, getting him more than 1,300 citations and H-index of 16. Also, I have been fortunate enough to have studied under his guidance during my master's. Today, Tekvani sir will share his experience on power quality issues in microgrid. Sir, we are delighted to have you with us. Thank you, and over to you, sir.
Yeah. Thank you.
Thank you, sir.
So I see around 46 participants are here. So it is good, and let us now start our session. I will share the file. Okay, is this presentation first slide visible? Title slide?
Yes, sir.
Yes, sir. Yes, sir.
My sincere request, when we have this particular presentation, you can keep your mic in mute mode, but of course you can definitely unmute it whenever you have any question. And you can interrupt me at any time, not necessarily at the last moment or last 5-10 minutes, but anytime during the session. If you want to interact, you can definitely unmute your mic and discuss. Yes. So now the point is power quality issues in microgrid. There are two things to be understood. One is this power quality. And other issue is microgrid. Now, whenever point comes in our mind that microgrid, that means we understand that it is mainly the use of distributed energy sources. And then using those distributed energy sources, whether conventional or non-conventional, we form a separate entity of power system, which is known as microgrid. There is a concept of nanogrid also. I think very few must have really heard about that. That like you have several nanogrids and then it forms a microgrid also. Fine. Now, power quality issues in microgrid. I have tried to give a holistic presentation here, starting from our non-conventional energy sources, then microgrid, its types, and then converters and their control for power quality. Let me ask a simple question here. Any participant can respond. When you respond, unmute and again mute your mic. What do you mean by power quality? Anybody can tell me. What do you mean by power quality? Yes. Any participant? Yes.
Sir, power quality means whatever supply we are getting, that should be at within the specified or the prescribed limit in terms of the frequency and the voltage.
Very good. So, power quality has anything to do with the quality of power?
No, it has, in true sense, it has nothing to do with the quality of the power.
Right. Basically, it's all about voltage and current, right? And when we say power quality means, see, voltage should be in balanced manner, no under voltage, no over voltage, no harmonics, no noise, intended frequency within the range, intended amplitude, intended shape, and also the current also within the prescribed harmonic limits. So this is what we mean by power quality. Am I right?
Yes, sir.
Yeah, fine. Okay. Now let's proceed. So we all know electric power generation because mainly we are all electrical engineers basically, or even if you are from electronics or IC also, you know the basic things. So either you have the normal fossil fuel like coal, gas, you may have hydro, even nuclear. Then here we have the wind and solar and small hydro also, which are falling under non-conventional energy sources, renewable energy sources, small hydro, wind, solar mainly. So nowadays, in order to meet the demands of our varieties of loads, it's recommended not only to be dependent mainly on the grid and keep on using this fossil fuels, but at the same time we can construct our small grids for our independent loads, and then if required additional power can be fed back to the grid. So that concept is very well known. Now there are certain figures which are true figures based on the source of Central Electricity Authority of India. The total installed electric power generation capacity of India in August 2021, you see here it is 3,88,134 megawatt. And then central sector, state sector, private sector distribution is given, and majority is private sector. See here. This number may be more today because this data is almost now you can say 4 months old data. You may say approximately we have 4 lakh megawatt. I think that we can say 4 lakh megawatt installed capacity. This is installed capacity. It doesn't mean that whatever is installed we are using it. Huh? So our total generation will be quite less than this one, but this is the installed capacity. This numbers and data is very useful for any electrical engineer to know before we really move to our microgrid concept. And this is the seminar of microgrid, so I thought you must be aware about these basic facts. Even anywhere you go, if you have this basic idea, you can be confident enough to discuss these issues. So 4 lakh megawatt. And installed power generation capacity in India, fuel-wise now, if you see, this is also from Ministry of Power, Government of India. Fossil fuel, total fossil fuel, 2,34,000 megawatt. See, that is 60% of total installed capacity. And non-fossil fuels, and where here you have hydro, wind, solar, and other renewable energy. And total non-fossil fuel percentage is approximately 40%. So see, we are in the ratio of 60-40, fossil, non-fossil. Ratio of 60-40, fossil, non-fossil. Can we make 40-60? That is very interesting question. Instead of this 60-40, you can see here, this is 60%, this is 40%, and then 100% total. That is same 388,134 megawatt. So 60-40, can we have 40-60? And if it is 40-60, what does it mean in future to come? That we are less dependent on fossil fuel, carbon footprint will reduce, and more renewable energy sources will be used. Not only that, but when you have more renewable sources, say wind, solar, other, these are the sources now from where you don't get continuous energy. This is fluctuating energy. That's the problem. Because when major portion of your generation is by such kind of variable sources, then grid stability and maintaining the demand is difficult. And that is why the role of engineers will increase. Here all the engineers who are sitting and participating in this FDP, our role increases because now we have to penetrate more and more renewable energy into the grid, which is not which is basically a fluctuating and not constant source, and it increases the challenges. So electric power generation through renewable sources, if you see year-wise, percentage of renewable energy with respect to total generation, that percentage is increasing. See here, it is increasing in a good fashion, and you see 1920, almost 10% of total generation is by renewable energy, almost 10%. You see the capacity, installed capacity is almost 40%, but generation is only 10%, and that's the thing you should understand. And this source is annual report of 1920 Central Electricity Authority. I have personally gone through these reports and then taken this data. So I'm sure that data which I'm presenting is correct from these references. So here, 10% of renewable total generation, and that is in 1920. But good thing is that it is increasing here every year. So total generation, millions of units, if you see here. So this many units, which is 10% coming from, 10% of total coming from renewable energy sources. Fine. So even the conclusion is even 40% installed capacity, the contribution is hardly 10%. So source-wise breakup of cumulative renewable energy generation from April 19 to March 20. The major proportion comes from wind and solar. The first one is wind, 46% of the share of renewable, and 36% from solar. Then you have small hydro, biomass, bagasse, and others. So this is the total, picture. So we see that wind and solar are predominant. They have the maximum share from the renewable energy sources, and that is why mostly we concentrate on this wind, solar, and in the coming years also their installed capacities are still going to increase. So others are of course there, even nuclear, but that's fine. Uh, Here is the major share. Source wise breakup. So here the 87,000 megawatt, which is there total, out of which 43% from wind, 39% from solar, and small hydro, biomass, bagasse, and others, and waste to energy. So here also, if you see, the main source is wind and solar, and it is obvious because their installed capacity is also accordingly. So India's renewable energy sector at a glance, this is what I was telling, that in 1920, our contribution in generation from renewable is 10%. In 2021, up to December 2020, it was 11%. And that is also increasing, see this, right? So maybe now up to December 2021, it will be approximately around 12%, and it is still going to increase further. So it is very clear that percentage share of renewable energy generation is increasing, quite evident from the figures. Their installed capacity is also going to increase in future. Its total share in overall power generation is definitely going to increase. This is data from MNRE, Government of India Annual Report. Now see the top 10 states in solar installation capacity in megawatt. Now the first one is Karnataka, Rajasthan, Tamil Nadu, Telangana, Gujarat, Andhra Pradesh, and so on. And this is from MNRE Annual Report 2021. So these are the 10 top 10 states. So others are also there, but then their contribution is very small. These are and this is mainly because of natural climatic conditions, land availability, and some policies and other things. But overall, if you see now here, these are the 10 states in India contributing into the major portion of the installed capacity of solar. So capacity in megawatt. So here, this is as far as wind is, solar is concerned. Now, see the wind. Wind power potential in India at 100 meters and 120 meters above ground level. Again, the top 7 states: Andhra, Gujarat, Karnataka, Madhya Pradesh, Maharashtra, Rajasthan, Tamil Nadu. And wind power potential at 100 meter above ground level, 120 meter above ground level. This total 7 windy states, and all India total, if you see, so this total 7 states generate the wind potential having gigawatt 292, whereas all other states only 9 gigawatt. So that is why here is the major potential. Wind power potential at 120 meters above ground level. So now we understand that where is the potential, solar potential and wind potential, major states, and this is also from MNRE annual report. So the windy states and their capacity, if you see, installed capacity, all is shown here: Andhra Pradesh, Gujarat, Karnataka, and all other states here. And others are only 4.3 megawatt. See, and where the total is 38,624 megawatt. So it means that we are dependent mainly on these states, basically, as far as wind power generation is considered. Okay, so I understand now that this has given a fairly good idea about our solar and wind generation capacity. Evolution in the size of commercial wind turbine, if you see, from 1980 to 2020, power, diameter, and height. So the diameter is increasing, and if you see now the radius of these windmills, even in the radius, the Boeing 747 plane can be accommodated lengthwise. That much is the radius of the blade here, and the power capacity is increasing for windmill from say 50 kilowatt. Here it is 50 kilowatt, and gradually it increases. Now it goes to 15 to 20 megawatt also, and height is somewhere around 200 to 250 meters. That's it's a very good height. So understand that the individual wind turbine capacity is increasing. Its diameter, its power, its height increasing. So what is there to support that? Because you cannot directly use this power. This power is to be processed by power electronic circuits. And therefore, the converter which is used in power electronic control of this wind turbines should be capable of handling that much high power. Now, here is the point. Say, for example, 7.5 megawatt, but then you need a 7.5 megawatt converter also, sometimes less also, to extract the power. And that is, very, very important that and nowadays the power electronic converters, not only IGBTs, but silicon carbide, not only silicon, but silicon carbide devices. Very recently, I was reading a paper from one of the manufacturers of silicon carbide devices, that how silicon carbide devices are going to change the technology of electric vehicles. In electric vehicles also, a large number of SiC devices, MOSFETs and IGBTs are being used. Similarly, here in wind converters, for very high power capacity, we have to use silicon carbide devices. We have to use multi-level converters and not the conventional converters. And because of that only, it is possible to handle that much amount of high power. That is to be understood. So the reference is given here. This is from the proceedings of the AICTE. Okay, now what is our national scenario? So in 2022, electrical power targets include achieving 175 gigawatt. And then the government further revised it to 227 gigawatt of energy from renewable sources, out of which 100 gigawatt will be from solar, 60 gigawatt from wind, 10 gigawatt from biomass, and 5 gigawatt from small hydro. Additional 31 gigawatt from floating solar and offshore wind powers. So this is the target. And the target is revised and increased. So altogether now, we are going to have 227 gigawatt of power from the renewable sources. And that's great. And these numbers are going to increase further in future to come. So with this, we are very sure that in coming days, we have to deal with solar and wind power definitely in more and more, power handling capacity. Okay. The reference is given. It is the Ministry of New and Renewable Energy, Wind Energy Division, National Wind Solar Hybrid Policy. This is a policy published in May 2018. Okay, so now focus on electricity generation through renewable energy sources. So here we see we have solar, we have wind energy, regulation and conversion, we have battery bank. Here we have a generator also, AC or DC, and then the load. So now the concept comes here, and then concept of microgrid. Concept of microgrid comes into picture. So where is the power electronics in electricity generation by wind? For example, here I am showing a system: windmill, wind turbine, generator, transformer, and then transmission line, grid, and load and distribution transformer. You don't see any power electronics here, but it is there. Without power electronics, it cannot work. So wind energy conversion system is composed of several components that convert wind kinetic energy into electric energy in a controlled, reliable, and efficient manner. So now different kinds of wind generators. As you know, squirrel cage induction generator, wound rotor induction generator, double fed induction generator, wound rotor synchronous generator, and permanent magnet synchronous generator. So you have varieties of generators available. I am not going to discuss their merits and demerits because that will take us to a different route. That's not the discussion of the topic today. So here you know that you have varieties of generators and they have got their merits and demerits. Power converters, of course, filters are there. Harmonic filter, that is the generator side, and this is grid side. You have a step-up transformer and then the grid. But here you have the power converters also, where you can see you have IGBTs, you have GTO, you have diodes, and then coupled inductors and capacitors. So mainly either GTOs or IGBTs are used, and different types of converters are used. Different topologies of converters are used. Converters for microgrid are different, and converters for medium voltage, high power grid are different. Here, the topologies of converters will be different from power rating of the grid. Reference given. So what is power electronics? We know power electronics is a technology that deals with the conversion and control of electric power with high efficiency switching mode power semiconductor devices and electronic controller for a wide range of applications. And applications are many, whether it is VAR compensation, harmonic compensation, HVDC, flexible AC transmission system, photovoltaic fuel cell power conversion, high frequency heating, motor drive, electric vehicles, and so on. So today it's a golden age for power electronic applications in this particular areas. And especially right now we are talking about smart grid and microgrid. So in that also power electronics has major role to play. So here that is what I have tried to put it into one slide, that what do we really mean by power electronics. So the heart of power electronics is a digital controller here. Then you have the switching devices, either IGBT or SCR or even GTO. This is a very high power device. This is medium power device. This is high frequency device. This is low frequency device. Opto isolation. And then large number of applications are here, whether it is wind or it is solar or EV or motor control or lighting control or whatever it is. So the conversion AC to DC, DC to DC, DC to AC, and AC to DC, AC, AC. So then accordingly the names are there, whether it is inverter or rectifier, cycloconverter or matrix converter or chopper or PWM inverter or whatever it is. You know, but mainly they are converters. Converter is a general name, but then it can be inverter, it can be cycloconverter, it can be chopper. Here in our microgrid applications, what we are going to see mainly the use of DC-DC converters, DC-AC converters. These are main converters because the input from solar is DC, which is coming to the system. So you need DC-DC converters. Most of the time, boost converters. Then this DC is to be converted into AC for AC microgrid. So DC-AC converters. That is inverter. Okay. So in order to work with any application, and here our application is microgrid. For power electronic circuits, you need to have knowledge of circuit theory, systems and control theory, signal processing, electronics, electromagnetics, power system, machines, simulation, solid state physics, and many more. Digital signal processing, digital controllers. And then only a working prototype of even microgrid is possible. Because in microgrid also, we have to apply the concept of control, concept of signal processing, concept of solid state physics, control theory, and so many more. So now see here, a doubly fed induction generator based wind energy conversion system. Here is the power electronics. Somebody, I was just discussing now that where is the power electronics. So you have the pitch angle, wind turbine control, gearbox, doubly fed induction generator. So you have the stator and you have the rotor here because doubly fed induction generator. And now in the rotor side, you have a rotor side converter. And at the grid side, because this is grid here, you have a grid side converter. And both the converters have their own controllers. And then sinusoidal pulse width modulation or space vector pulse width modulation, any technology can be used in order to control this. And they have got intermediate DC link. It's a huge capacitor sitting here, which makes this as a stiff DC link. So DC link voltage is being sensed, and then you have the filters, and then currents through the filter you are sensing. You are operating this as a current control converter or voltage control converter, depending on the application. So now you have the control coming into picture here. But this is in general I am showing. Now the beauty of these converters, whether it is the generator side, that is a converter, or it is a grid side converter. So here one thing to be understood is that at the rotor side converter here and generator, the grid side converter, both these converters are bidirectional converters. That is most important thing, and that you can see now current is bidirectional here also. So by controlling them, we can appropriately control the power in both the directions, and that is the very flexible operation of these converters. It leads to flexible. IGBT is a bipolar device. Name itself says insulated gate bipolar transistor. It has got reverse conducting diode, which is integrated in the device. This is not separately put, it is integrated in the device. Okay. So microgrid. A microgrid is a small scale power system with a cluster of loads and distributed generators operating together through energy management software and devices that act as a single controllable entity with respect to the grid. Now see this 4 lines definition. You have to break it into the parts. Read it again. Microgrid is a small scale power system. First is small scale power system with a cluster of loads. And distributed generators operating through energy management software. You need energy management software in order to generate power optimally from this microgrid. And devices that act as a single controllable entity with respect to the grid. Now this is the definition of microgrid. There are several definitions of microgrid, but I am just presenting here a particular definition. You may have microgrid definition at in different ways, but this is one. But then it serves the purpose very clearly that small scale power system, cluster of loads and distributed generators operating together through energy management software and devices that act as a single controllable entity with respect to the grid. Very nice definition. Participants, there is one more request from my side. Generally, it is there that, okay, we will get this PPT. So what is there? We will simply listen and then spend the time here. I suggest that we should have note-taking abilities also, note-taking habit also. So all the time now, when you come across in such kind of lectures, something useful, interesting, you should note it down. So yes, anybody wants to say anything?
Yes, sir, very true.
Yes.
You very rightly mentioned the tendency which nowadays we are having.
No, everybody, I am also with you. We are all teachers, and we many times listen such kind of seminars. Not only you, I also listen many seminars, programs, such kind of events. But it is always useful for us that if we keep taking some notes. Anyway, I will give this task, the PPT, but many times, we get PPT, but then we do not use it much. But then if we keep on noting something, no, it goes directly into our brain. And that has long-lasting effect. That's why I'm saying. So microgrid has become a key research element in smart grid and distribution power systems. Nowadays, a lot of research is taking place in microgrid. Even if you see IIT Bombay, IIT Madras, uh, IIC Bangalore, and many other such reputed educational institutes, a lot of research is going on in microgrid on several research problems of the microgrid. Many faculty members and research scholars are working. So you may also identify some such problems of microgrid and start working on those as your research topic. If you are a PhD holder already, you can give such problems to your research student, or even if you are working on PhD or yet to work, you can take some of this as your research problem. Microgrid mainly contains different renewable energy sources that use various technological advancements such as power electronic based technologies. Nowadays, power electronics is inevitable in case of microgrid. But not only power electronics, there are so many other technologies also used. A lot of communication is also used. A lot of software is also used because you have now the energy management software. I already said here, see it is written, energy management software. And it works as a single entity. When can it work as single entity? When you have the communication between this. So communication engineering, control engineering, software engineering, power electronics engineering, power system engineering. See, so many areas are there to contribute. And then whatever is your favorite area, you can choose and work on it in this microgrid domain. How it has, however, it has an unstable output, obviously, because mainly wind and solar, thereby causing different types of power quality events. अब देखिए यहाँ से शुरू हुआ. How seamlessly I am integrating now, you see in this lecture that initially we had discussion about the capacity of renewable, then microgrid, and now we are moving to the power quality. So it has an unstable output, thereby causing different types of power quality events. We say it is event only. In power quality, whether it is sag or swell or harmonic, these are called events. Power system engineers will know this in a better way. These are PQ events, power quality events. As a result, standards and mitigation methods have been developed in recent years. देखिए एक तो microgrid itself, even though it's a microgrid, it is very complex. Then how about our normal grid? That is much more complex, because I was reading somewhere that which is the largest man-made machine, and that is electrical transmission line. Am I right? All electrical engineers?
Yes, sir.
Yeah, of course, there are several machines, and we do not underestimate the efforts of other fields also. Every engineer has to contribute. But just for an example, that electrical transmission line is a huge machine, man-made machine. But microgrid also a machine where you need knowledge of varieties of fields. And as a result, standard and mitigation methods to avoid these PQ events have been developed in recent years. Microgrid is a smaller version of the subsisting centralized electricity system, because microgrids too regulate and distribute the flow of electricity to consumers like the subsisting power grids. So It's a small entity, but then it has so many features, so many issues, and we engineers have to deal with those. We have to improve it and propose the solutions. So type of microgrids: AC microgrid, DC microgrid, a hybrid AC-DC microgrid. See AC microgrid here, wind power or photovoltaic system. See here. So if it is wind power, it is AC-DC AC converter. Why I am saying AC-DC AC converter? Yes, if you see here, just a minute. Yeah, this is AC-DC AC conversion. Am I right? See, this is AC. This is DC. And this is again AC. So if you have a wind source, definitely you need AC-DC AC conversion. So that is what is said here. This is AC-DC AC. So basically AC to AC converter with intermediate DC link, stiff DC link. You have DC input, then DC AC converter, DC AC converter inverter basically. And then you have AC microgrid. Grid is here, diesel generator. Now you have to feed to the load also. So suppose it is DC load, then again you need AC to DC converter, that is rectifier. Or directly you can feed some AC load, or you have commercial load or residential load. See, and here the only link which is bidirectional is this. Can you see this? This is bidirectional. So this way your load is to be driven through AC microgrid. This is now series cascaded AC microgrid topology is also seen here. At the point of common coupling, you see this is wind turbine, this is energy storage source, that is our battery, let us say. It can be battery, it can be supercapacitor, it can be fuel cell, then PV panel, and it's a series cascade arrangement of the cells. And finally, you construct one AC microgrid. Simple. Merits of AC microgrid. The pronounced advantage of an AC microgrid is the use of transformer with high efficiency. By using transformer, AC microgrid's voltage can be stepped up or stepped down for distribution purpose and for the local loads present near the microgrid. So suppose you want to respectively, so that respectively has the meaning that voltage can be stepped up for distribution purpose and it can be stepped down for local loads through a transformer. Because of periodic zero voltage crossings, protection schemes for AC circuits are advantageous because switching circuit breakers extinguishes fault current R at zero crossings. Yes, obviously. So merits of AC microgrid, mainly the protection scheme for AC circuit are advantageous because of natural zero crossing. Continuing with this merits, by controlling reactive power independently, stable voltage can be obtained. See, that is the advantage. You can separately control the reactive power through your control logic. In grid-tied mode, when any fault condition occurs in microgrid, then AC microgrid will disconnect itself. AC load receives direct supply from AC microgrid, and they will not be influenced from the disturbances occur in main grid. Very, very important point. See, when any fault condition occurs in microgrid, then AC microgrid will disconnect itself and AC load receive direct supply from the microgrid. So they are not influenced from the disturbances in the main grid. So your critical load remains unaffected, kind of islanding mode. But every system has got some demerits also. So AC microgrid has also got demerits. AC power must be transmuted into DC loads such as battery charging, computers, DC fluorescent lamp, etc. Hence, efficiency is reduced due to this conversion. But nowadays we have got very good conversion efficiency of these power electronic converters. But still there is some loss. Use of power electronic converters introduce harmonics in the main grid. Yeah. And that's why we need to use filters. And also, because these are all hard switched converters, so they will definitely introduce harmonics. But then we have to use filters, and also many times we use active power filters. Interconnection of DC renewable source is not simple, because DC output of these sources must be converted to the AC through inverters. So inverters will come into picture. Definitely. So whenever you want interaction with DC loads and DC source in AC microgrid, you need converters. That's as simple as that. Correct? Yeah, but then similar will be true with the DC microgrid also. At the other hand, so DC microgrid, you have wind here, then rectifier, DC microgrid, then you have photovoltaic, DC AC converter. But here you can have DC to DC converter also, and that goes to DC microgrid, grid, bidirectional AC DC converter. So this is bidirectional now, where power flow can reverse also. DC load directly fed, DC DC bidirectional converter for battery, because it has to get power from the battery and it has to charge the battery also. Suppose when there is no power available here, definitely you can use battery bank as the backup. So you need to charge the battery and you can get battery as a source also. Then DC AC, then it can feed to AC load. So here is inverter. And electric vehicles can also be fed to the grid. So this is a DC microgrid. Merits of DC microgrid: battery storage system can be connected directly to supply backup power. Yes. Backup storage system will supply power during peak load period or in the absence of any distributed generator. See here. So there are two purposes of this backup. When there is a sudden high demand during peak load period, so those kind of contingencies can be met with this battery backup. Not only that, now one good thing is that this kind of electric vehicle, please understand, this is shown only unidirectional. But why can't it be bidirectional? What is that? Suppose this vehicle is fully charged and it is connected to the grid here. So whenever there is a huge demand and it is to be supplied, let us say, to the load, and you do not have sufficient power here, here you have some power, but then you can use this power also, because they have also got a fully charged battery banks inside it, which you may not need immediately. Suppose the vehicle is in parking condition for several hours. Why don't we connect it to the grid, so that not only charging, but if sometime there is a contingency demand, it can be met by the vehicles. That's possible. And this is also good area of research. Because The way these battery banks are available, here also battery banks are available. So this only cannot be bidirectional. This can also be bidirectional. Possible. Of course, with proper rules and regulations. Those things will come into picture. But as an engineer, we can think about the possibilities. So, DC microgrid during peak load or in the absence of any distributed generator, the energy storage system can be used. Direct interconnection reduces multiple power conversion and improves the efficiency of the system. Yeah. So less the number of converters, more is the efficiency, more is the reliability also at the same time. So direct interconnection helps reducing multiple power conversion and increasing the efficiency. Easy interconnection of renewable energy sources. So DC grid has got these advantages. Continuing, battery storage of DC microgrid will regularly provide power to load if there is any power disruption in the AC main grid. Yeah, because you have battery bank. The power converter loss and operating cost of DC system can minimize because only simple inverter unit connected with AC main grid is required. Simple inverter. And you know, nowadays the efficiency of these inverters, oh, it's you please note that the efficiency of these inverters is more than 97, 98%, almost 99%. So the power loss is fractional now. These inverters are very, very efficient. That's why only using inverters, this DC grid is advantageous. Further DC merits. In present power system structure, most of the load unit require AC power. So only DC distribution network is not feasible. Voltage transformation in DC system is less systematized as compared to AC system. And to transmute AC power to DC power rectifier is required for the integration of AC generators. Well, these points are not directly as merits, but I should consider these as demerits. Understand? If they are not merits, they are demerits, actually speaking. But fine, these demerits are not those, very severe demerits. Then hybrid AC-DC microgrid, another model possible. Wind power, and you have AC-DC, AC as we discussed. Diesel generator, grid, AC load. So here is a bidirectional, see. And this side you have DC microgrid, photovoltaic, DC load, battery, and vehicle. So both systems are now made available here. And in between you have bidirectional AC-DC interlinking converter. See? Great. So that means now you are integrating both and making it as a hybrid grid. Ultimately, which is connected to the grid, main grid. So this is hybrid microgrid, which is then connected with the main grid. Everything now integrated here. Are you getting it? So does it make sense? Up till now, any of the participant, if you have any point, please let me know. I will just have some water, but tell me if you have any point. Yes, any point? Anybody? Because this is
any question,
hour.
any question from participants?
We have reached half the mark, so any point? Does it make sense? Is it interesting? Because now from here only you have to find out your research problems. Okay, so we proceed. Questions are generally asked in last 5 minutes, but those last 5 minutes never come, huh? I tell you.
Yes, sir.
Because everybody is in hurry at the end, because the new speaker will arrive and this speaker has to go, and then you also need a break. So then what suffers is the question answer session, and that is why most of the time I request that participant can ask question at any time during the lecture. Okay, so AC/DC parallel microgrid topology, as we just saw here, we have DC microgrid here, we have AC microgrid here, and then you integrate them. Here you have the point of common coupling at the utility grid. So, and this is the interlinking converter. That is what is said here, AC/DC interlinking converter. And this converter, the beauty of this converter is it is bidirectional converter. And in our laboratory also, practically we have worked on such kind of bidirectional AC/DC converters, where bidirectional power flow is demonstrated. And it can work as rectifier, it can work as inverter also. It all depends on the condition and the power flow. So your control logic should be able to operate it in both the directions. That's possible. And these are all IGBT based PWM converters, mind well. Now those phase control rectifier and all that time has gone. And even you have the rectifiers, these are all PWM rectifiers. So everything is now pulse width modulated IGBT based converters. So components in a microgrid, you have the distributed power generation, wind, solar mainly, power electronic converter, load, storage device, battery mainly, control algorithm, and point of common coupling. So these are the 6 major parts of a microgrid. And each has got its own role. And now you have to see where you can contribute. Either you can contribute in power generation, or you can contribute in power conversion or control, or even at load side management or at the grid side management. That is all possible. So what is the need in modern present power system scenario? Renewable energy sources are becoming most paramount energy sources due to the increased awareness on environmental issues. Yes. Also, the power generation capacity of distributed energy resources is low. This low generation ability has incentivized the need for integration of various types of distributed energy resources and loads in the form of a microgrid. Now, microgrid converters, there are 4 major types of these converters. One is called grid forming power converter. Second is grid following power converter. Third is grid supporting power converter. And fourth is interlinking power converter. See, grid forming, grid following, grid supporting, and interlinking. Yes. And depending on this converter types, only you have the control of these converters. So grid forming power converter, the first one here, grid forming power converter. Grid forming power converter in islanding mode, converter are accountable for maintaining reference voltage and frequency in case of AC subgrid. देखिए grid because they form the grid. The converter itself is a grid here in a microgrid. So islanded operation, AC grid or DC microgrid. So if it is islanding mode and AC microgrid, so these converters are accountable for maintaining reference voltage and frequency. Yeah. And if it is DC subgrid, then they are maintaining reference voltages. So that is the point. AC and DC subgrid. So AC voltage and frequency, DC voltage. We all know this. If it is grid connected mode, this power converter adjusts the active power in case of DC grid and active as well as reactive power in case of AC grid. देखिए, very important. Now, if it is DC grid, only active power, but then reactive power also comes into picture in case of AC subgrid. To keep the state of charge of the energy storage system units and at times to enhance the voltage profile in case of DC subgrid and power quality in case of AC subgrid. तो यही तो आपकी power quality picture में आ रही है, देखिए. From here itself the power quality starts. Power quality is not seen nowadays separately. देखिए, yes, we are going to see some of the power quality issues, but mind well, power quality issues require remedies. So remedial measures are to be applied. But why to apply remedial measures if I can control my converter itself that there is no problem of power quality? This is understand now another way of dealing with the problem, that why you apply the remedy if you can prevent that at the converter level itself. So not the remedial measure, but I mean to say not the corrective measure, but you use it or you apply it in such a way that it itself is not generated. So you can eliminate that, and that is why here in grid connected mode, the active and reactive powers are controlled to enhance the voltage profile in DC grid and power quality in AC grid. That is very important. So you prevent the power quality problems instead of solving the power quality problems. New definition is like that only. Of course, dynamic voltage restorers, active power filters, then the unified PQ controllers, those are there. But instead of them, now if your converter itself is capable of controlling these parameters, why to use separate measures? That is the point. And there you need more sophisticated control of your converters in a microgrid. These grid forming converters operate in voltage control mode so that the voltage and frequency in AC grid and voltage in DC grid can be controlled. So they are all voltage controlled converters, voltage controlled voltage source converters, and to control the voltage and frequency. Then you have the grid following converter. This the previous one was grid forming. You can see here, no? Grid forming. Now we say grid following. Now grid following. This type of power converters are associated with the non-dispatchable distributed generation, that is solar and wind. These converters continuously follow the grid reference voltage and frequency in the case of AC subgrid and inject active and reactive power to achieve unity power factor. देखिए, so it solves the power quality problem because your power factor is unity. Most of the power quality problems start from non-unity power factor. And the power factor definition, please understand that most of the time no definition is considered as cos phi, but no, that is only displacement power factor. The real definition of power factor is the dot product of distortion power factor and displacement power factor. So in order to make power factor unity, it's not sufficient that displacement power factor is made unity. but distortion power factor is also made unity. And that is done, distortion power factor, either through filters or by PWM schemes in the converters. See that what I am saying is a complex task. Making power factor unity, you need to make cos phi as well as THD. So THD you say 0 and cos phi unity. And, so THD 0 means distortion factor here what we are saying. So if the both are unity, then overall is unity. So in the same way, in the case of DC subgrid, it injects current or power into the grid while following the grid reference voltage. Though these converters follow the grid reference values, so this type of converters are treated as a controlled current source consisting of high impedance in parallel. So these are current sources, previously current control sources, previously these were voltage control sources. Then you have the third category, grid supporting converters. Sometimes the grid forming power converters are failed to maintain the pre-assigned voltage and frequency in subgrids due to limited reserve capacity of power to be delivered or absorbed by the energy storage systems. Are you getting it? So if the grid forming converters fail to maintain the assigned voltage of the value of voltage and frequency, then what to do? So some additional dispatchable DGs or energy sources used to support the grid forming converter to retain the assigned voltage and frequency in AC and voltage in DC grid in the islanding mode. Yeah, we know that. So you need to support the grid also. So in that case, whatever energy storage system you have, you can use that. So for that also you have the converters. वो आपने देखे ना इधर, you see here. For example, you have the battery bank. Now in that battery bank, you have this converter. See, so they are supporting, right? So this is grid supporting converter. And this in grid connected mode, these converters provide support for improving the power quality in case of AC and voltage profile in case of DC. Whenever you say there is a sudden power demand and or even the reactive demand, then you have to supply that demand. If the reactive demand is not met, then you know suddenly there will be under voltage. We know that. So under voltage is also an event of power quality. So in order to stop that event occurring, we need to definitely use the grid supporting power converters. That's what now. That is what I was telling, that why can't our electric vehicle also becomes grid supporting power converter? Here, this has to support the grid also. It's not only the load, and then it can become a bidirectional. Here also there will be an arrow, right? Yeah, that is all. So these converters are considered equivalent to a controlled voltage source or current source associated with low or high impedance in series or parallel respectively. Well, so you can use them either in current control mode or voltage control mode. Now the fourth one is interlinking power converters. An interlinking power converter, that is this one. As you know, this is interlinking power converter. So interlinking power converter, the fourth category, is generally used to interlink DC subgrid with AC subgrid to form the AC-DC microgrid. Yes, that's what we saw in the block diagram. capable of bidirectional operation based on the surplus of power on a particular subgrid. Yes. So here energy management comes into picture. That the interlinking converter is a bidirectional converter. Can operate in inversion mode or in rectifier mode or stop mode. See? Then this interlinking power converters can also fulfill the purpose of grid forming and grid supporting power converters. Sometimes they can work as grid forming or grid supporting power converters also. However, the literature presented some severe issues such as non-linear load behavior while performing power flow from AC subgrid to DC subgrid, circulating current between parallel operated interlinking power converters, and resynchronization issue after fault clearance. These are the problems with interlinking power converters, but then they are to be dealt with by the researchers. So I hope that I am giving you a very clear idea about a microgrid and where the problems can be. Okay, so now come to power quality. Power quality encompasses the characteristics of the electricity at a given point on an electrical system evaluated against a set of reference technical parameters. High quality microgrid output power can be ensured by focusing on main issues related to voltage sag, voltage swell, voltage and current harmonics, system unbalance and fluctuations. अब यही तो है. These are the only points in which you have to focus and devise the control strategy of your microgrid in such a way by using all these four types of converters: forming, following, supporting, interlinking. So there will be a primary control, there will be a secondary control, there will be a tertiary control also. Understand that microgrid, that's why I am saying that this is also a complex control mechanism. In order to avoid all these power quality issues, either you have to put a primary control, not either, you have to put all three: primary, secondary and tertiary control to control these power converters. So what I'm saying here, high quality microgrid output power can be ensured by focusing on main issues related to voltage sag, voltage swell, that is amplitude, voltage and current harmonics, system unbalances and fluctuations. So we need to get rid of these events. So power quality coverage issues in microgrid, if voltage quality you see here, voltage variation, voltage unbalance, harmonic distortion of voltage waveform and phase balancing continuity, phase balancing. So these are the problems. Then continuity of supply, type of interruption, duration of interruption, voltage level of fault, type of continuity indicator, and here the commercial quality, the quality, it is commercial transaction between an electricity company and a customer. So how are these things interrelated? Quality of supply, voltage quality, there are standards. I take example of IEEE 519 2014, 1992 also, 2014 is the revised version, you all know this, where harmonic limits are given. But in a power system, we generally see the quality of voltage, but quality of current is also important, because depending on the harmonics drawn by the current by nonlinear load and depending on the system impedance, there will be a voltage drop. And based on the order of those harmonics, the harmonic voltage drop in the line impedance will distort the line voltage also. That depends how significant is the current drawn from the source. So there are two kinds of I must say the requirements. One is requirement of voltage quality, that is the responsibility of utility, and the current quality is the responsibility of the user. But now microgrid here, the utility and user sometimes may be same. That's the point. So in microgrid, the holistic definition of current quality and voltage quality, both have to be dealt with simultaneously. In our normal grid, the voltage and current quality, the responsibility lies with utility for voltage, and for current, the responsibility lies with user. User has no rights to inject harmonics, so that at the PCC, the injected harmonics will distort the voltage waveform, and the other person who is also supplied same voltage will also get distorted voltage. Are you getting it? But microgrid, the concept is little different. If it is islanded mode, yeah, if it is grid connected mode, the question is different again. But in grid connected mode, many times, the power coming from the microgrid is not that high level. So this small amount of power will be, dealt with by the huge power of the grid. So its quality may not matter much. But no, of course, we have to follow the norms. So power quality issues in microgrid: transient, impulsive, surge, oscillatory, short duration variation, sag, deep, swell, interruption, long duration, under voltage, over voltage interruption, imbalance of voltage and current, waveform distortion, AC offset, DC offset, harmonics, interharmonics, noise, notching, voltage fluctuations, and island. Now these are the issues. Getting it? So in islanded microgrid, PQ is a major concern in small-scale islanded system because of the presence of nonlinear and unbalanced load. Dekha? So you have a nonlinear and unbalanced load, let us say, which forms a large proportion of the load, total load. So if it is a significant load which is nonlinear load, then it will affect the entire voltage. That's what exactly I said just before a few moments. This situation creates voltage problems such as distortion, fluctuation, and voltage sag or swell in a relatively weak system. Dekha? In islanded mode. In the islanded mode, disturbances such as distortion and voltage unbalance are most likely to occur because of the very high impedance and the more uneven load distribution compared with the grid connected mode. Yes, यहाँ पे impedance is very high. It's not like our normal grid where impedance is so low that then if impedance is so low, so what will happen that the same amount of current will have less voltage drop, and hence the overall system voltage will be affected less. But here, as the impedance is more, even a small amount of current will cause more voltage distortion. That's the point. आप समझ रहे हैं? See what I'll just a minute. Let me go back to one of the slides here. I don't know where it is. Just a minute. Here it is. See. So what I'm saying, you have to see this. This is microgrid. This is PCC. And here is your grid load, and then this is the impedance. But now suppose it is islanded mode, then this is not there. And you have only the load. At that time, this impedance is large. But when the grid is available, definitely, after that load is seen, the impedance will be very, very small. So that's the point what I wanted to say, that in the grid connected system, the impedance is different. And then in the islanded mode, the impedance is different. So, that's what very high impedance and more uneven load disturbances distribution compared with the grid connected mode. So in islanded mode, you have the problem of voltage distortion. That's the point. In the grid connected mode, disturbances such as unbalanced utility voltages and voltage sag are the most frequent problems. The voltage generated from the sources such as wind, solar, fuel cell are highly intermittent, and thus these sources cannot be connected directly to the grid. Yeah. So what are these power quality problems? You see sag here. This is sag. Then you have swell, unbalanced voltage, imbalance is there. One phase voltage is much compared to other two. Fluctuations are there. And then their description is shown here, indicators, causes and effects. For example, sag. Now, what is the cause of the sag? We understand that there are some high power losses or can damage the microgrid's power electronic devices, speed loss of motors. These are the effects. And what is the cause? Energization of heavy load. Yes, suddenly you are putting heavy load on, then definitely, let's say for example, very heavy motor is starting. Motor starts, it draws very high magnetizing current. And that magnetizing current will cause the voltage sag in the system. Then voltage swell is also there. When de-energizing the heavy load, you will see the voltage swell. And here unbalanced variation in the load, large single phase load is there in the system, that will also create imbalance, or unequal load distribution will also cause the voltage unbalance. That will reduce the equipment life, increase cable losses, inject more harmonics, phase fault and poor inverter efficiency. Fluctuations, mainly repeated on-off of electrical motors or oscillating loads are there. Some intermittent loads are there. So because of that, you will have so all these problems are to be eliminated by using proper control mechanism in our converters now, instead of putting remedial measures. Then harmonics. So these nonlinear loads are causing harmonics. Electronic inverters, computer drives, variable speed motors, all will generate the harmonics. And because of this, reduce the performance of energy generation, distort the microgrid's output AC sine wave. You have the super harmonics also. These are from 2 to 150 kilohertz. Because switching of power electronic devices, especially inverters and modern sources. So this kind of high frequency switching of power electronic converters will also introduce super harmonics, which is supra harmonics. But now these are all the effects, power quality issues. So what we do, we can use custom power devices, ABC, DVR, APC, and DStatCom. So hierarchical control, if you see, robust optimization based harmonic mitigation method. So here what we do is, we can use any of these devices, AVC, DVR, APC, DStatCom. For example here, see this is series parallel active power filter. So you have the series compensation, you have the you have the series compensation, you have the parallel compensation also. Then you have full power back-to-back converter. So they are back-to-back converters. And then you can have the control of power in either direction. Then here you have the energy storage, then the distributed, just say wind generation, say solar generation, then you have the load, and then you have the coordination also. So you have the secondary, then you have the remote sensing also, and you have to integrate now all these solutions together to make that as a single entity. अब यही तो बात है कि भाई now PCC will see this complete form as a single entity. This complete as a single entity. So PCC will not understand, okay, where is your source and where is your compensation. Finally, you will see here, it's as a single system. That's the point. So active voltage conditioners you can use. And in here you have again one H-bridge inverter. And you see that it is coming in series and you are conditioning the voltage at PCC. Dynamic voltage restorers are there, DVR. So DVRs can also provide the compensation in the voltage. Then you have active power conditioner. So as I said, it is AC, DC, DC, AC bidirectional. So either you have the shunt compensation or you can have the series compensation also. Both are possible. Voltage compensation, current compensation, or harmonic compensation is also possible. Distribution static synchronous compensator. So D statecom is also used here, which can also compensate at the PCC. So there are different mechanisms available. They have got their own control mechanism, their own control flow chart, and you can use them. So as a summary, see, this is no custom power device, let us say. Then voltage THD is 15%, current THD is 26%, because heavy non-linear load. And because of high impedance, the voltage THD is also more. But now if you put AVC, then it goes to 3.98 and this goes to 4.6%. Percentage of fundamental. THD is always percentage of fundamental. DVR 4%, 4%, APC 3%, 2%, and these two statecom 4%, 2%. So different remedial measures, different custom power devices will be able to solve these issues at different level. And which control strategy is used, what kind of fastness of control is used, they will decide all these numbers. But fine, so ultimately it shows that you can use any of these custom power devices depending on your application. So robust optimization based harmonic mitigation method, you have the primary controller. So here is your space vector or sinusoidal pulse width modulated DC to AC converter. So the DC, the AC basically it is inverter. Then you have the filter, line impedance, and this is PCC. So you are sensing the current at PCC, you are sensing the voltage at PCC, and then you have the droop characteristic of the controller, the reactive power and voltage and reactive power and frequency. They are relevant, you know. So this droop characteristic curves are used here. And then ABC to alpha beta, and here you have the current controller, you have the voltage controller, and in this current control and voltage control loop, finally you are deriving the signals to drive the converter. So I mean to say that you can define the droop characteristic here, and accordingly you can make your converter operating depending on the system parameters so that proper power quality is ensured at the PCC. It is what is to be done. So if you see here, now I can make my converter itself operating on this algorithm. I do not need a separate power device, custom power device. That is also possible. So that is called multifunctional converters. So nowadays, a lot of research is happening in multifunctional converters also. Secondary controller is also there. Here we saw the primary controller, right? As I said, no? Primary control, secondary and tertiary control also. So secondary controller, you are using the optimization techniques also in the secondary controller. And DG1, DG2, individual control, filter, line impedance, and THD of all the buses. So microgrid buses, THD sense that all. And then you can have the optimization algorithm also operating. And then conventional droop controller, voltage reference generator, so PQ calculator, and then droop controller is there. Then you have some gains, and from the feedback signals of voltage and angle, you can have the voltage reference generator. So it's called VDR. So droop characteristic of every generator is to be understood for that. And what is the limitation that you want to put on that? Based on this, you can define your droop controller. This particle swarm optimization algorithm used at secondary level, that was this one. Which flow chart is given? Well, you can have your own flow chart also. As you know, it determines the P based and G based as it is done generally in PSO. And using that, you are generating the pulses for the converters. So there are many more. I am just giving you a few examples here. Then this is another type of grid here, typical structure of microgrid. Then see the DG1, DG2. So what is that? The optimization control scheme, that you have the local controller, you have dual optimization algorithm also. See, so they are interconnected now. They have local control here, that is here, DG1, DG2, but they are interconnected also. This is what the initial definition we saw, that they are all seen as a, they are all applied with the energy optimization software also, so seen as a single controller. So here you have the central control unit, which optimizes. I'm just showing you two examples, but there may be DG1, DG2, DG3, 4, and DGN also. That's the point. Here is the droop characteristic. So active power frequency droop characteristic. Similarly, reactive power voltage droop characteristic can also be seen. And you have, say, for example, different you know, PV, fuel cell. So for that you have different characteristics. And in that, where you want to put the limit in this droop characteristic, based on that you have to generate the reference voltages of the system. And your control algorithm has to work. So for example here, PV, battery and fuel cell. So frequency limits are shown here, F minimum, F reference, F high, F max. So battery and PV units operate together under adequate illumination. Then battery and fuel cell unit operate under extreme weather conditions, and the PV cannot output power. So if the PV is unable to give, then what is to be done? Then battery and fuel cell. And battery, PV and fuel cell units run together under insufficient illumination or heavy load conditions. So all three inputs have to. So it all depends what kind of algorithm you are fixing in your control loop, and correspondingly the optimization is to be done. So conventional and smart grid comparison is there. Smart grid has got self-healing, where conventional grid you need the manual restoration. Self-monitoring is also possible. So nowadays our microgrids, we want to make them as smart grids. So more and more communication, as I said, see, digital and two-way communication. So you need now these grids to communicate, so it becomes a smart grid. And these types are already discussed: hybrid, AC, DC, high frequency, low frequency, system structure, supervisory control, centralized, decentralized, distributed, many such things here. So understand that now what we have to do, we have to put a proper control logic in order to decide the operation of all these converters. I want to come to a very nice example. These are okay. Then you have the see, yeah, this is what I was telling about: the primary control, secondary control, and tertiary control in the distributed energy unit. And then a peer-to-peer overlay network is also there, where you have the communication network, and this is your LV grid. So mainly what we are doing here is, first is the power reliability loop. So power reliability, so active power, reactive power, voltage and frequency are the parameters here, and this is called primary control. Definitely primary control is the most important control for us, that is to be given to a microgrid. Then you have the secondary control, is mainly for power quality. So first you make it reliable, then you make a quality one also. So these are the secondary parameters. And then tertiary, the economic parameters are also there, that from which particular source you input the power so that economically it is more viable. So inter source communication is important. Deciding the priorities is important. Deciding the power quality parameters is important. And primarily that what sort of voltage and currents, as well as the voltage and frequency ultimately, and then active and reactive power you need. So each one will have a different control algorithm, and using the algorithm like this, which I was just discussing here, you have to. So ultimately the algorithm remains this, but now whether it is the primary or secondary or tertiary, depending on that, there will be some varieties. That's the main point to be understood in any microgrid system. There are large number of such control algorithms. I am just showing here a few, but if you see the literature, you will find varieties of such algorithms, hundreds of different block schematics you will find, and each and every paper will claim something different. That is obvious. That is the research. Okay. We were here. Yeah. Okay. So, nutshell, this is very important: primary control, secondary, and tertiary. Primary for power P, Q, voltage, frequency, then power quality parameters, and then economical parameters. So, the primary controller is used to provide reliable operation and to respond to communication failures. It is associated by frequency and voltage as inputs, and it gives control action, that is Q primary and P primary, to control the deviation of the voltage and frequency. That's what we know: reactive power for deviation of voltage and active power for deviation of frequency. The secondary controller is used to regulate the voltage and frequency on the basis of its response to the load and supply changes. देखिए, supply keeps on changing. So its control action P secondary and Q secondary are given by calculation of the average of primary control actions. And the tertiary control is used to improve the operation of distributed energy resource units so that they have an optimal cost efficiency. That's what I said. As far as the power limit allow the distributed energy resource to exchange their power at equal marginal cost. So there are also a lot of softwares, optimization softwares coming into picture. So that is tertiary control. Primary, secondary, tertiary. You have got algorithms for all the three, and then you have to integrate, and finally a microgrid works. And not only that, apart from this, you will have the individual control algorithms also of a subgrid 1, subgrid 2, subgrid 3, and so on. Now understand how complex is the system. So even though it's a microgrid, but its complexity is not micro. So this is a two-level grid-connected inverter with LCL filter, and in closed loop control you have to operate it. So it depends what kind of converter it is. Either you operate it into the voltage source converter in voltage control mode, or voltage source converter in current control mode. So the inverter control algorithm will be like this. So you have the grid here, and from this grid you are sensing the current, coupling in inductors are there, voltage, LC filter. This is our inverter, and you have two loops. One is the inner current control loop and outer voltage control loop. So this is the current feedback, and here is your reference current, and similarly here you have the voltage control loop where you have got the actual voltage C coming here, and you have the reference voltage from here. So this will give these are basically PI controllers, mind well. Most of the time these are PI controllers. So they generate and this is power controller. So they generate reference voltage. Here it generates reference current, and finally you have the control signal for PWM inverter. So wireless network is also there, and from that you get the signals, and then you have the P and Q signal, and which is given to a power controller. So this kind of control algorithm will be there invariably in each inverter circuit which is connecting to the grid. So grid code requirements are to be satisfied. To ensure the grid stability and consumer power quality, many specific technical requirements, often called grid codes, have been developed and regularly updated. The main element in the grid codes include active power control, so as to adjust the grid frequency, reactive power control to regulate the grid voltage, grid power quality, flicker, harmonic, fault right-through operation, and system protection. So you have to take care of these things in your algorithms in order to see that there are no power quality issues, there are no fluctuations, and required voltage and frequency are generated. So some of these standards, I discussed about this IEEE standard 519 1992 and 94 also. You can have a look on this IEEE and IEC standards. So mainly this is harmonic requirements by 519. Yeah, we all know this. And even if you do not know, you can just go to IEEE and download this standard. Then power quality requirements are mentioned in 1159. Then there are IEC standards, say 61,000 series, very important. This series is so important that it is referred in so many applications. Here also harmonic current emission limit, flicker and fluctuation meter, compatibility rates for low frequency induced disruptions. So many of these standards are followed in our microgrid. Here I was saying that DVR integrated microgrid system to mitigate PQ issues. So our conversion system, you see battery or solar, then this is the load and grid. So here is our DVR. Can you see this? So series compensation we are providing in order to mitigate this power quality issue. This is a general equivalent circuit. Similarly, here you have the state form. And here you have the UPQC. Now UPQC is again a bidirectional one. And you have the series as well as the shunt compensation. See, the holistic compensation. So it's a typical UPQC configuration for microgrid also. Overall structure will be like this. Very complex one, even if you have, this is only one microgrid, subgrid. Then there are many other inverter classes and configurations, which I will now avoid because you have many PWM schemes and others. But I would like to draw your attention to, yeah, the solar cell arrays and all, and their configurations, their string and other things I will not discuss right now. You know that multi-string and centralized and AC modules and their merits and demerits are discussed. That is fine. But then lastly, I would like you to see one thing here. This is a 9-level inverter in a microgrid system where you have the boost converter, multi-level converter, and you have the MPPT algorithm here, and multi-level inverter grid tied controller is here. So this particular scheme is, topology is used so that the harmonics are reduced. Mainly the multi-level inverter topologies are adopted to reduce the harmonics at the output voltage. So no specific measures are then required to be taken when you are integrating it with the grid. So that's the advantage, the topological advantage. And like here it was seen, no? So the output voltage will be something like this. This is very good. And then you don't need much filtration of this one. So that's the advantage. Then this is kind of active power filter to compensate the harmonics. Now this is very interesting. This is called multifunctional double mode inverter for power quality enhancement. Now see here, you have this floating interlude boost converter. This is a normal boost converter. And you have the solar input. So, you know, generally we boost it. Now for battery here, we are putting the bidirectional DC-DC floating interlude buck boost converter. That is this one. So this is buck boost converter. Now this buck boost converter is used to charge. It's a bidirectional. So either it can go this way or it can supply to the inverter also. Now this inverter is a multifunctional inverter. It can be used as a active power filter also, and it can be used as inverter to connect it to the grid also. Because mind well, this solar in the evening hours, you know, it is of no use. So there is no power coming from here. So at that time, of course, battery backup is here. So you can use this as battery, or even you can use as a power quality improving device for the grid. So that is the concept used, and that is why you see instantaneous reactive power theory is available. So this instantaneous power theory makes this particular inverter to operate as active power filter. So it's a unified controller, and this even it has got the PLL logic also when it is operating this grid synchronization as inverter to give the power from the solar. So this is the portion which it operates like inverter, and then here this is the portion that it operates like the active power filter. So details of this can be understood, but now this multifunctional inverter, in addition to load grid requirement, the proposed multifunctional dual mode inverter can operate within the following 8 functionalities: harmonic compensation and reactive power injection, harmonic compensation and active power injection, active power injection, reactive, active and reactive, harmonic compensation, active and reactive power, and harmonic compensation, store the PV module energy into the battery. So these are the different functions of this inverter. So that is why the multifunctional inverters are nowadays very popular in such kind of applications where power quality as well as normal operation both are taken care of by the inverter. So that is I wanted you to understand. Now lot of research is involved here, so you can decide that what kind of functionality you want from your inverter, because power circuit is same. Now only by defining your control algorithm you can operate it as a filter or as active or reactive power controller. So that's the thing. And now here any of you, if you have any point, please discuss, because I have now some references which I am putting here for your information. And some references are given in the slides also. And with this, I thank you all the members here. And the last 5 minutes, 4-5 minutes you have, if you want to have any question or anything. Yes, so it's open for discussion, please.
Yes, participants, if you have any question, any query regarding what the Tekvani sir has discussed on power quality issues, their causes and solutions, please you may raise the question and queries. He is ready to take up the questions.
And see, the queries will be there, even you can discuss and ask, but finally you have to simulate and experimentally work on it. Then only the feel and then understanding of it comes. And first simulation is very, very important, because in simulation, all are numbers actually, whether it's kiloampere or milliampere. So you can play around with the system parameters in simulation and learn more. Then you can implement. Yes, tell me, any question?
Yes, participants. Any
How many,
question?
how many would be, really practically implementing it, because that is more important. Even a small microgrid, even islanding mode is also sufficient. And then you see large number of, control algorithms, even not grid connected. Islanding operation is also wonderful to be implemented. Yes. Okay. So if there are no questions, fine, because questions may not immediately arise sometime, when you really start working, and then more questions will come. But you can refer many of these papers available and try to learn more from this. In different algorithms, say whether it is instantaneous reactive power theory or synchronous reference frame theory or DC link regulation theory or space vector based pulse width control, active reactive power control, all these algorithms are available, or even you can have your own modified algorithm also. But then you have to apply to these inverters and learn more about this. Okay. If there are no questions,
Sir, there is one query in the chat box.
Tell me, what is that?
Frequency regulation through grid feeding inverter is possible in microgrid. That question is asked by Ms. Hetal.
Yeah. See, this is very interesting question. Why I'm saying that question is a very appropriate question, that frequency regulation possible in microgrid through the microgrid inverter in the grid. So in grid connected mode, it depends that what significant portion of your power is coming from that microgrid. Then only the frequency regulation can be considered, because then you need more and more active power to come from microgrid. And in that, it has got its limit, because the overall grid capacity is how much and microgrid capacity is how much. That decides the level of compensation. But yes, it is possible, but up to an extent which is basically governed by the power level of the microgrid into that grid. Yes.
Mr. Nikunj, you have written in the chat box that working of multifunction double mode inverter. I think the question is not clear. What actually you would like to ask? What is your query, and what would be your expectation? Please be elaborative.
Sir,
Yes, yes.
sir, I want to know about that. How does this dual mode inverter you have just in this current slide? How it is works? I want to understand that.
See, this dual mode inverter is like that. This inverter now can support the active power and reactive power, the PQ components of the power. That is one. So we see here that VD and VQ components, ID and IQ components, and based on that you can control the PWM signals of this inverter in order to control the active and reactive power to the grid. But then there is another scope here, which is the instantaneous reactive power theory. Now, what are we doing by this theory? That you have the reference currents of harmonics also. So you can sense these currents here, and you can extract the harmonics. And what it will do, PQ theory, it will generate the reference currents which are in the phase opposition of the harmonic currents. So now this will also give the command to this inverter to generate those harmonic currents also. So what will happen, that you can cancel it out, those harmonics, and you can operate it as a power quality improving device also. So it is in your control algorithm that how you want this particular inverter to operate. Yes.
Thank you, sir.
Yeah, this is, see, exactly that is what we do generally by active power filter. See, when you have active power filter, it generates the reference compensating current by instantaneous PQ theory, which your inverter has to follow, generating the actual compensating current. And then the grid current can be made sinusoidal. So there are some other nonlinear loads on this grid, and because of that, here the PCC is distorted. So if you can eliminate those harmonics by your inverter, then the burden on the grid will reduce. That is the point. So it is called multifunctional. Yeah. Any other problem?
Sir, there is one question from Mr. Rakesh. Which system is more effective and reliable between AC and DC?
See, nowadays, a very good question again. See, nowadays we have varieties of loads. Even now, your EV charging stations will also come into picture. Even your battery banks are there. Even power quality issues and active and reactive power issues are also there. So, looking, and then not only that, your sources are also AC and DC sources, because solar DC source, wind AC source. Definitely, that's why most of the time we have to go for hybrid systems, AC, DC, microgrids, not the individual ones, with the interconnected, interlinking power converters. So practically, the grids are to be now hybrid grids. That is the suggestion. Yes. Because why I'm saying there are two benefits. Interlinking converters are very, very efficient. That is one. So there is no much loss. But another important thing is that these interlinking converters are bidirectional converters. So active reactive power both can be controlled, and then a lot of power quality issues can also be solved. That's the point. And that is why we need to go for hybrid systems. Yes.
Yes, we'll be taking last question.
Yeah.
From Mr. Uvesh, how to address the issue of supraharmonics?
Supraharmonics. Yes, that's what. See, supraharmonics are basically from the hard switched converters, which are switched at very high frequencies. Now, for this supraharmonics also, in our control strategy of active power filters, there is a separate control algorithm which I have not yet discussed in this presentation. But then you have to extract this supraharmonics depending on the switching frequency of your inverter. And in this switching frequency, you have to produce again the harmonic component in your active filter, which can compensate this supraharmonics. But mind well, the supraharmonics are in the range of very high frequency. A small amount of filter, switching filter, can also eliminate the supraharmonics. So that is also possible. It is not demanding much heavy filter. So small LC filter will also work. But if you do not want to use it because of the passive components, then you can go for the algorithm where the harmonic extraction algorithm is used, which is discussed in several papers, in order to generate the harmonics to oppose the supraharmonics of the switching frequency of inverter. But that is only possible when it is operating in the voltage control mode. Mind well, if your converter is operating in current control mode, then again harmonics are not fixed. Then online extraction of harmonic is to be used in order to eliminate this supraharmonics. But then for that the algorithm is available, which makes your system more complicated. So many a times people do not deal with the supraharmonics, and they say let them be there because the system impedance itself will filter it out many a times because they are high order harmonics. So let your system impedance filter it out, or you can work with it. But if not, then you can eliminate it by the algorithms. So these are the three ways to do it. Yes.
Okay, participants, now if you have any question, you can send us to us, and then we'll route that question to Tekvani sir. Tekvani sir, thank you very much. He has started with the very basics of the generation capacity, and then gradually he has taken us to the more complex structure of the control of the control and the different algorithms of the power quality. So he has discussed very wide spectrum that involves in the microgrid as well as the common power system. We are very much thankful to Tekvani sir, as because he is a very busy schedule, and he has spared more than 2 hours in discussing, and even during the question answer session he has quietly explained the questions of the participants who have asked the questions. So thank you very much sir for your time and your knowledge which you have shared with us today. We are very much thankful to you.
Yeah, thank you at the same time, and then thank you all the participants also. See, this requires a lot of patience also while understanding the concept of microgrid. And then, even though, as I said, it is microgrid, but then the things are not micro associated with it because you have varieties of controls coming into picture. And that is why I took it from very basic, and then gradually we went up to the final one where the entire control comes into picture: primary, secondary, tertiary. And that too, I was just restricting up to block diagram. But now when to go into the details of it, writing the algorithms and tuning the algorithms and PI controller, each algorithm itself is a task. So that is why a lot of patience is required while working with it, and it's not advisable to work on the entire, but you can take a part of the problem, and then that part you focus and do your research.
Yes, absolutely true sir.
Yeah, that is what is required. and then you decide that on which part you want to do your further research.
And in a way that you have touched number of different aspects and avenues for the research also, directly and sometimes indirectly also. So that may give some clicks to the participants, those who are interested to work in the microgrid area.
Very correct, yes. So okay, thank you.
Okay,
Now
thank you very much, sir. Thank you very much, sir.
Okay.
Now participants, the third session of today's will start at 2:30 sharp, and that will be on the introduction to the smart grid technology, and that will be discussed by Dr. Premalata Jaina from IIT Roorkee. So we request you to be on time at 2:30 sharp. Thank you. Moreover, please don't forget to fill the forms for the session 2 of this session. And then we have a break up to 2:30.